In this section of the course, we'll learn about C++ functions. Functions allow us to divide our programs into modular units of executable code and call and reuse these units as we wish. Functions are a very powerful abstraction mechanism. You've already seen functions defined, the main function that we've been using in every program. And you've also used some functions such as getLine and the C-style string functions, string copy, string length, and others. In this section, we'll understand what functions are and why they're so useful. Then we'll look at functions in detail. First, we'll see how to define functions and create function prototypes that make our functions useful anywhere in our code. As we've already seen, when we call a function, we usually send information to the function. This information is sent in the form of function parameters. We'll see how to define these parameters and exactly how they work. Functions also usually return some kind of information to us when they're done processing. For example, if we have a function that calculates the square root of a number, well, that function expects the number, and it will return to us the square root of the number, which we can use however we wish. Functions can also take many parameters, and in some cases, we want to default the value of some of those parameters so we don't have to provide them every time. We'll learn how to set these default values per parameters to make our code easier to write. Then we'll learn how to pass arrays to functions and how to work with them inside the function. I'll discuss references in the next section, but we'll look at how we can pass information to a function efficiently by avoiding copying. We'll also see how we can change passed information as well as protect it from change. Then we'll discuss inline functions. Inline functions are functions that the compiler optimizes to avoid the overhead involved when we call functions. Remember when we use the auto keyword to allow the compiler to deduce the type of a variable? Well, we can also use the auto keyword to allow the compiler to deduce the type of the function return value. This is pretty cool, and it can save us from writing a lot of unnecessarily complex code. Finally, we'll learn about recursive functions. These are functions that call themselves. You might be wondering, why would a function call itself? You'll see, it's pretty cool, and it can help solve a class of problems that would be more complex to solve without recursion. At the end of this section, we'll do a challenge project, and we'll be well on our way to starting to learn object-oriented programming. Let's get started. In this video, we'll learn about what functions are in C++. When we develop C++ programs, we typically use the predefined functions and classes in the C++ standard libraries. These are functions and classes that have already been written for us and tested, and they're available for us to use. We've already seen how useful the standard vector and standard string classes can be. C++ has many other libraries that we can use in the same way. Depending on our application, we may also use third-party functions and libraries. These may be open source, commercial, or other types of libraries that have been developed by other programmers and are available to use in our applications. So if we want to develop games in C++, we'd very likely use third-party libraries or frameworks such as Cocos 2DX, Unreal, Spring, CryEngine, or others. Why would we use third-party libraries? Well, that's pretty easy, because these libraries take a tremendous amount of effort to develop, and chances are high that the functionality you need has already been implemented and tested and ready to use. So why reinvent the wheel? Reusing existing functions and classes from existing libraries is great. But even then, you still need to write your own C++ functions and classes that are specific to the problem you're trying to solve. We'll talk about classes and object-oriented programming soon. In this section, we'll focus on functions. Functions allow us to modularize our program. This is a big deal since we can divide our program into logical, self-contained units of code that we can reuse whenever we need to. Let's see a simple example. On the left-hand side of the screen, you can see a program written in the way we've been writing them up to this point. Lots of statements, one after the other. Some of these statements might be if statements, some might be looping statements, but you can see that this program has three logical sections, one for input, one for processing, and one for output. But everything's in the main function. This is okay for relatively small programs like the ones we've written, but as programs get larger and more complex, this breaks down quickly, and the code becomes difficult to manage. Also, we tend to copy and paste code a lot since we may need the same functionality in different places in the program. There's a field in computer science called software engineering. Software engineering is all about designing your solutions and writing your code in a way that can be easily understood, debugged, and extended. One of the fundamental principles in software engineering is abstraction. Abstraction is exactly what functions help us achieve. Let's look at the example on the right side of the screen. In this case, we've replaced 10 statements with 3. These 3 statements are function calls. Now, when we look at our main function, we see less detail, more abstraction. We can now see read input, process input, and provide output. So we've modularized our program. We know that we still have to execute all the code we had before, but we've removed it from main and replaced it with a call to functions in each case. Let's see what these functions look like. On the left side of the screen, we see the same main function with the 3 function calls. And on the right side of the screen, we see the implemented functions, read input, process input, and provide output. Notice that each of these functions executes the same statements that we were executing previously in the main function. This makes our code more modular, more readable, more maintainable, easier to debug, and easier to reuse. Let's see how this can help us develop programs. A common analogy that's used when learning about functions is the boss-worker analogy. Let's assume you're the boss and you need to get a task done. This task involves several subtasks, and your job is not to perform the individual subtasks, but to coordinate the execution of those subtasks and report the synthesized results back to your own boss. So you've hired 3 workers that have expertise in each of those subtasks. So you assign a subtask to each worker and provide each of them whatever information they need to perform it. Since each of the workers knows exactly what to do, when they complete their subtask, they report their results back to you. This may simply be a comment that says, "I'm done," or it could be a complex report that they created and provide to you. Now that all subtasks are completed, you look at the individual results, synthesize the report, and give it to your boss. Sounds like an easy job being a boss, right? Actually, no. The boss needs to know what worker to assign the specific subtask to, the order to do them in, the information to provide to each of them so they can do their job, and the boss needs to know what he or she is getting back in order to synthesize it and report back. This is a great analogy to using functions. If you need to call functions, you write your code to the function specification. You need to understand what the function does, you need to understand what information the function needs, you need to understand what the function returns to you, you need to understand any errors that the function may produce and why, you need to understand any performance constraints, and so on. What you don't need to worry about is how the function works internally, unless of course you're the programmer coding the function. This is super important to understand. When we use string, vectors, math functions, complex image processing libraries, collision detection in games, we don't need to know how those algorithms work. This concept is called information hiding, and we'll revisit this again when we talk about object-oriented classes. Let's see an example of this. C++ has many libraries. One library is a mathematics library. In order to use this library, we must include CMath. The CMath library has many mathematical functions, including trig, exponential, logarithmic, power, rounding, and many more kinds of functions. These functions are global functions, which means they're available to the entire program. We call these functions by using their name followed by a series of arguments. In the output statement on this slide, we're calling square root and we're passing in 400.0 to it. The square root function will calculate the square root of 400 and return the result which is printed. In the last example, we're calling the power function, which expects 2 arguments. In this case, we're calculating 2.0 raised to the 3.0 power. Notice that to use these functions, all we need to know is what they do, their name, what they expect from us, and what they return to us. How the square root or the power is being calculated isn't something I need to know to use them. That's classic abstraction. There are many built-in functions and classes in C++. However, we'll need to learn to design and write our own. In this section, we'll learn to write our own functions. Here's a preview of a very simple function so you can see where we're going. Don't worry about the syntax, I'll cover all that later. In this case, I have a function called addNumbers, and it expects 2 integers named a and b. The body of the function simply returns a plus b. So we take the sum of a plus b and return the result to the caller. Notice the int to the left of the function name. That tells you what the function returns. In this case, an integer. Pretty easy, right? Now every time we need to add 2 integers, we can call addNumbers and supply the 2 arguments that the function expects. Then I can do whatever I want with the result I get back. In this case, I'm displaying it. I know what you're probably thinking. Why in the world would I write a function that adds 2 numbers when I can just use the plus operator? Well, normally you wouldn't, but suppose we had a requirement that if any of those numbers is negative, then we must return 0. Let's see how we can modify this function. So this is what the function might look like if we had to return 0 if either a or b is negative. It would probably be a good idea to give this function a better name, but hopefully this preview example gives you a good high-level view of a simple user-defined function. Let's head over to the IDE and use some of the functions in the C++ standard library. Before we learn to write and define our own functions, it's important to understand to use functions that are already defined for us. I've opened up a browser and I've gone to cppreference.com. I'm going to show you 3 pages within this website, and I'll provide URLs and the resources for the course. Here I'm going to the C++ standard library header files. Here are all the standard header files in C++, and you can see there's a whole bunch of them. This would become your next learning experience in C++. Once you understand the basics of the programming language, once you understand object orientation within C++, then it's a matter of learning what's out there and available to you. There's a lot of stuff out there and there's a lot to learn, but don't worry, you won't learn it all at once. You'll learn it little by little as you use C++. What I want to do here is I want to talk about a couple of libraries, and we'll run a couple of example programs using those libraries. We'll use some of the functions in those libraries. The first library we'll use is the math library, and I've got a pane open right here to the CMath standard library header. Now we're going to use some of the functions in here. You can see that they're all defined, and if you need information about any of them, you can just click on here and you can learn about them. We're going to use the square root, the cube root, and the power function. They're just like what you would think, right? You pass in a number, you get the square root. You pass in a number, you get the cube root. And in this case, I pass in 2 numbers to the power function, and it will raise the base to some exponent. And here's a whole bunch of information about those functions. Okay, we're also going to do sine and cosine, and a couple of other interesting and very useful functions: the ceiling, the floor, and round. The ceiling of a floating point number is the next integer. So if my number is 12.4, the ceiling would be 13. The floor is the other way around. So if I have 12.4, then the floor will be 12. And rounding works just like you would expect. 12.5 rounds up to 13, 12.4 rounds down to 12. So that's what we'll do. And then in the next little program we'll write, we'll come to the C standard library, and I'll open up that website for you as well. This is C standard lib. That's the name of the library header. That's what you need to include. And there's a couple of functions in here that we'll use, and I'll scroll down just a little bit. They're right here. It's rand and srand. Rand generates a random number, a pseudo-random number, and I'll explain what that means in a little bit. And srand seeds the random number generator. So what we'll do is we'll use this function, rand, to generate the number. Let's say we're rolling a 6-sided die and we can get something between 1 and 6. We could really make that between anything and anything, and I'll show you how to do that. And then we'll seed that random number generator so that the patterns of numbers we get will differ every time. So I'm going to head over to the IDE now, and we'll start with the math functions. Okay, so I'm back in the IDE, and I'm in the section 11 workspace in the math project. And here we're just doing some real simple math examples to show you how to use these functions. First of all, we're including CMath. That's required, otherwise you're going to get a lot of compiler errors because the compiler won't know about square root, it won't know about sine or anything else. In this little example, I'm declaring a double called num, and I'm asking the user to enter that number. Once the user enters the number, I'm simply calling the square root function that will return the square root of the number, and we'll display it right in line. The cube root, the sine, the cosine, the ceiling, the floor, and we'll round that number. Then after that, I'll ask the user for another number, which I've defined called power. In this case, we'll raise that number that they typed into this power. So if they typed in 2.5, we'll raise it to whatever power they wanted to. And again, here what we're doing is we're calling the power function right here, and we're passing in the number and the power to raise it to. Pretty simple. You can see from this code, I don't know how square root works or cube root works or sine or cosine or power. I don't know how this stuff is implemented behind the scenes. That's the whole point. I don't care. I don't need to know. And this is where abstraction really shines, because we're just trying to solve a problem. And I know I need to raise something to a power, or I know I need a sine or a cosine. I can simply look up the library, understand how that function is being called, understand what that function returns, and then just use it and use the result. So let's run this program. And let's say the number we enter is 125.6, and I'll press enter. So the square root of 125.6 is 11.2071. The cube root we expect to be right around 5, right? Because 5 times 5 is 25, times 5 is 125. So that gives us, it's not a formal test case, but it's a pretty informal test case that makes us feel good that our code is working. Here's the sine of the number, the cosine of the number. Now the ceiling of 125.6 is the next integer up, which is 126. The floor would be the integer down, which is 125. And in this case, we round 125.6 up to 126. So let's enter a power. Let's raise this to the 4.2 power. There you go. That's a pretty big number. So 125.6 raised to the 4.2 power is 6.54269 times 10 to the 8th. There you go. We've used the math functions without knowing anything about how they're implemented. That's a real powerful place to be. Let me go back to the IDE now, and we'll create some random numbers. Okay, so I'm back in the IDE, and I'm still in the Section 11 workspace. This time I'm in the random project. Now, in order to use random numbers, I'm using the rand function. Now, the rand function has been used a long time in C++ and in C as well. But there's a better way to create random numbers if you're really doing statistical processing, and that's the random header file. I'm not going to cover that. I'm just going to use rand since that's what we're learning about calling functions. But if you really need very precise distributions, consider using the random header file. Okay, so in this case, we're including the C standard library. That gives us the rand function. And we're also including the C time library. I'll talk about that in a minute. In order to use random numbers, we really need to seed a random number generator. Now, what's a random number generator? A random number generator is just a generator that creates random numbers. Computers are real bad with random numbers. We have what are called pseudo-random numbers. What that means is that the numbers themselves are random, but the sequence that they're generated in is not. So in order to create more real random numbers, we want to seed that random number generator with a different value each time. That way it creates different sequences of values. So we'll do that in a second. I'll do it without seeding and with seeding so you can see the difference. But let's talk about what's going on here. I need a random number generated, right? So I'm going to create a variable called random number, and I'm initializing it to 0. And then what I want to do is I just want to loop and create 10 random numbers. And that's what my count variable is. I can make that as whatever I like, but in this case, it's a 10. And then in this case, I'm assuming we're rolling a die. So I want to return a random number between 1 and 6 inclusive. So 1, 2, 3, 4, 5, or 6. This could be 1 to 10. This could be 1 and 2 if you're flipping a coin. This could be anything you like, whatever range you like. This is how you would create that range. And I'm just going to create min and max to be 1 and 6. You can modify those to whatever you like to create whatever range you need. Okay. Now, the rand, if you look at the rand function in the documentation, it says that it returns a random number between 0 and rand max. I have no idea what rand max is on my system. It'll probably be different on your system, but it's guaranteed to be at least 32767. So I'll run it here and we'll see what we get. Now this function right here is the one that's seeding the random number generator. Remember, we want to seed this random number generator with a different number every time that we run this program. So what better way to seed it than with the system time? And that's what's going on right here. I'm seeding the random number generator to, I'm calling the time function and passing in a null pointer, which is 0. This line of code right here, you can see an example of that in the docs that I showed you earlier. It shows you exactly how to seed the random number generator. So now we've seeded the random number generator. And what we want to do is we want to generate 10 random numbers. So I'm going to start from I equals 1 while I is less than or equal to count. So I'm going from 1 to 10 by 1. There's my increment. And then each iteration of the loop, I'm going to call rand. Rand returns a number between 0 and 32767 or higher in this case. I have no idea what rand max is on my system. We'll see in a minute. I need to really scale that number down because I only want numbers between 1 and 6. So if I take rand and I take the modulus of it based on max, right? So take rand, divide it by 6, and whatever the remainder is, I've scaled that number down now. So in this case, if I divide a number by 6, the remainders are either going to be 0, 1, 2, 3, 4, or 5, right? Those are the only options I have. But since I want to go 1 to 6, I just add min to it. And it's as simple as that. So that's going to give me a number 1 through 6 inclusive. And I'm going to output it. So let's run this program and see how it runs here. I'll build and run. And rand max on my system is 32767. So now we know what it is. And here you can see that I'm generating 10 random numbers 1 through 6. So I'm getting 2 2s, a 5, a 3, a 1, a 2, and so forth. If I run this, remember the first sequence there is 225. So let's run this again. And now I've got 463 as the first 3 numbers. And I'll run this again. And now I've got 221 and so forth. Now, if we did not seed that random number generator, let me comment that line out right here. If I don't seed that and run it again, you can see 66556, okay? Let me run it again, 66556. So you see the numbers are random, but the sequence that we're getting is not. We're always going to get the same sequence of numbers. Now that can be useful sometimes if you're trying to repeat experiments and so forth, but usually you don't want that. And that's why we seed the random number generator here. So there you go. You see a couple of examples of using some built-in functions. We use the math library, and we're using the random number generation library, and we're using the C standard library to generate random numbers. None of this do we really care about how the random number generator works, unless that's what really interests you, and you can dig into the libraries and see exactly what algorithms they use. But if I need to create random numbers, this is how I do it. Really easy. In this video, we'll learn how to define our own functions. Function definitions have four main parts. We'll look at the syntax of functions in the next slide, but for now, let's look at what these parts are. The function has to have a name. The name of the function follows the same rules we use for naming variables. Function names should be meaningful and provide the reader the intent of the function. For example, a function called func1 and another function called func2 may be okay when teaching functions in my slides, but what if I read some production code with function names like that? I'd have no idea what these functions are doing based on those names. Functions perform operations, so usually you see function names as verb or verb phrases. This isn't always the case, but it's a good habit to get into. The second part of a function is the parameter list. This is the list of variables that the function expects from you when you call it. For example, if you're calling a function that adds 2 integers, then the 2 integers are in the parameter list. Sometimes functions don't need any parameters at all. Suppose I have a function that simply displays hello, or a function that returns a system time to me. These functions can be called with an empty parameter list. All functions have the ability to return information to the caller of the function. In order to return information, we must specify the type of that information. So I might return a Boolean or an integer or a double or a string. Also, it's possible that a function returns nothing. For example, if I need a function to just display hello, I really don't expect anything back from that function. In this case, we say that the return type is the keyword void. Finally, functions have bodies. These are statements to be executed and they're enclosed in curly braces. You've already seen an example of this in the main function. So as you can see, a function definition is pretty logical. The name of the function, what it expects, what it returns, and what it does. Let's see how this looks in C++ syntax. Here we have a simple function definition. Notice the name of the function is function_name. And after the function name, we have open and closed parentheses. In this case, this function expects no parameters, so there's nothing inside the parentheses. This function returns an integer. We specify that by providing the type of the return value before the function name. Finally, we have the body of the function, which consists of statements inside curly braces. You can see that this is the same syntax as we've used in our main function. Of course, we can have functions that return nothing, expect many parameters, and so forth. The syntax for all of them is very regular and exactly what you would expect. Let's see another one. In this case, we have the same function named function name, but this time it expects exactly one parameter. That parameter is an integer type, and it's available for us to use in the body of the function. In this example, we have a function that returns nothing when called. In this case, we provide the keyword void before the function name. This tells the compiler that there is no return type. With void functions, we can still have simple return statements in the body of the function, but they're totally optional and not often written. If there is no return statement, it's understood that the function returns after the last statement is executed. Pretty simple syntax. Let's look at one more. In this example, we see a function definition for function name that expects multiple parameters. In this case, the function expects 2 parameters, an integer and a standard string. When the function is called, these 2 parameters must be provided as arguments in the same order as specified in the parameter list. Suppose we want to write a function that displays hello followed by an end line every time it's called. We could easily define that function as follows. The function name is say hello, it expects no parameters and returns nothing. In the body of the function, we have an output statement that just displays hello. Notice that in this case, there is no return statement required since the function doesn't return anything. Once the say hello function is defined, we can call it from main or from any other function. In this example, you see the function say hello defined above, and you also see that it's being called by the main function below. This program will display hello. In this example, we're calling the say hello function 10 times inside a for loop in the main function. This will display hello 10 times, once per line. Of course, we can define as many functions as we need in our applications to help modularize our program. In this case, I'm defining 3 functions: say world, say hello, and main. Execution always begins with the main function. So in this case, main calls say hello. So we execute say hello, and we display hello to the console. But then say hello calls say world, and we display world. So this program displays hello world to the console. Here's the same example with some other output statements sprinkled in. Again, execution always begins with the main function. So in this case, main calls say hello. So we execute say hello. Remember that when say hello is finished, we need to complete the code in main. So we display hello to the console, then say hello calls say world. And when say world is done, we complete the code in say hello. So we execute say world, and it displays world to the console, followed by bye from say world. Then we go back to where we left off in say hello and execute bye from say hello. Then we go back to where we left off in main and execute bye from main, and our program terminates. You can walk through this code and you'll see exactly what's happening. There is one caveat about function definitions. The compiler must know the function details, that is, the function name, the parameters, and so forth, before the function is called. So look at this simple example. I'm calling say hello in main, but the compiler hasn't seen the definition of say hello yet. In this case, you'll get a compiler error telling you that say hello has not been declared in this scope. We'll talk about how to solve this issue with function prototypes in the next video. But before we do that, let's head over to the IDE and write a few functions. Okay, so I'm in the IDE. I'm in the Section 11 workspace in the Function Definitions project. What I want to do here is I want to write a program that calculates the area of a circle and the volume of a cylinder. Pretty easy calculations, but I want to bring up into functions that we define, create our own user-defined functions. And this is what I want my main to look like. 2 simple function calls: area of the circle, volume of the cylinder. That's it. Now within those functions, we can prompt the user to enter the radius, the height, whatever else we need. Okay, so let's get started. Let's write that area circle function first. Now in this case, I don't want to pass anything into the function or return anything from the function. This function is simply going to ask the user to enter the radius of the circle. It's going to call another function that will actually calculate the area, and it'll print the result. Okay, so let's write that function. We'll start with void since it returns nothing, and the name of the function is area of the circle. That's it. Simple as that. Nothing in the parameter list right now because we're not passing anything in, as you can see here in the call. Okay, so what do we need? Well, we need to ask the user for the radius of the circle, right? So we need a variable here, and we'll just call it radius. And double is perfect. We'll initialize it to 0. And we'll say, we'll prompt the user, and we'll put a new line at the beginning. We'll just say enter the radius of the circle. That's it. And we'll read the input into the variable we just created. You can see this pattern happening over and over again. It's pretty standard. Okay, now what do I want to do? Well, now I want to call another function that actually calculates the area. That function, again, remember the area for a circle is pi r squared. That function needs to know the radius in order to calculate the area. Let's write the function call first. We'll say something like cout. And we'll do something like, again, the area of a circle with radius, whatever they typed in. Now, that actually calculates that area and gives me back the double that I can display here. Okay, so let's call that function calc area circle. And that function expects the radius, right? And then we'll print a new line at the end. And really, that's it for this function. Let me clean that space up right here. All right. So now we need to write the other function, this function right here, calc area of the circle. Obviously, we need to return something from that function, right? The function is calculating the area, so it needs to return something to me so that I can display it here. So in this case, I want to return a double. And let's call it calc area of the circle. And what does it expect? It expects the radius, which is a double. What does it do now? It just returns pi r squared, right? Simple as that. But we haven't defined pi. Let's define it up here. We'll say const double pi, and we'll set it to 3.14159. That's close enough for this example. So there's my pi. It's constant, which is what we want. We don't want to be changing pi. And in the function body here, all we need to do really is just say return pi times the radius squared. We could use the pow function, or we could just say, radius times radius, which is what I'll do right here. That's it. That should do it. Let's walk through this. We call area of the circle, transfers control over to this function. We have a radius variable right here. We're asking the user to enter the radius of the circle. We're reading it, and then we're passing that value into this function, calc of the circle, and it's going to calculate the area of the circle and return that value back to me, which I'm going to print right in here. Now, I could store that into a variable or do anything I want with it, right? So let's run this and test it out. Oops, let me comment out volume of the cylinder because we haven't written that one yet. That's the next one we'll write. So the radius of the circle, 12.5. It says here the area of a circle with radius 12.5 is 490.873. Okay, obviously we'd want to test that to make sure that that's correct. And that's pretty much it, right? Pretty straightforward. Now let's write this one right here, the volume of a cylinder. Well, how do you calculate the volume of a cylinder? Well, the volume of a cylinder is pi r squared times the height of the cylinder, right? And I'm not using any units here. You can think of this as inches or centimeters or meters, or whatever you like. It doesn't really matter too much. So we need to write this volume cylinder function. This is going to be very similar to the area circle function, right? It's just going to prompt the user for some information. In this case, it's going to prompt the user for the radius of the cylinder and the height of the cylinder. So let's write it. We'll say void volume of a cylinder. And the reason that that's popping up in the completion is because I had that in there before, and I guess it remembered, which is kind of handy. All right, so we need the radius of the cylinder, and we'll initialize that to 0. And we also need the height of the cylinder. We'll initialize that to 0 as well. All right. So let's ask the user. Let me just copy and paste this to save a little typing time. So what is the radius of the cylinder in this case? And we'll read that into radius. Perfect. And then what we'll do here is we'll copy these guys as well. And we'll ask them for the height of the cylinder. Enter the height of the cylinder. We'll read that into the height variable. All right, so now we've got everything we need. So what do we do now? Well, let's do the output statement, right? We'll say cout, and we'll say the volume of a cylinder with radius, and we'll provide the radius value here. And then we'll say something like and height, and we'll output the height here. And finally, we'll just say, just like before, is. Now we need to call a function which we haven't written yet, right? So let's call it calc volume of the cylinder. We'll write that function in a minute. Now, what do we pass into it? Well, we need to pass in the radius and the height. Doesn't matter what order you put it in, but that's the way you have to provide the variables. So I could have said height, radius, and just sent in the correct ones. So in this case, I'm going to write that so it expects the radius first and then the height, and then we'll print a new line at the end, and that. Okay, so that's where we're at with this function. It's finished now, so let me clean up some of this space right here. Now what we need to do is write that function, calc volume cylinder. So let's do that, and we'll do it right here. We'll say, actually we'll do it a couple of lines up right under the other calculation right here. So we'll say double, because it returns a double, calc volume of the cylinder. It expects the radius, which is a double, and it expects the height, which is also a double. Right? So in this case, what do? We return pi radius squared times the height. And that gives us the volume of the cylinder. That should do it. We're calling volume cylinder now, so we'll do it 2 times. Now we'll get the area of the circle, which let's say it's, again, let's just say 10. And that's correct. That's what we expect, right? Pi times 100. So what's the radius of the cylinder this time? Well, let's say it's 12.1. And what's the height? Let's say it's a really tall cylinder, 25.2. So the volume of the cylinder with radius 12.1 and height 25.2 is 11,591. And we just need to put a little space after the is there. Okay, now there's one thing that we could do to make this a little better. You'll notice that this calculation right here, pi r squared, we're doing it again right here. So what we could do is we could refactor this code just so it's a little better, and we could say return, and what we could do is we can calculate the area of the circle and pass in the radius to it, and then multiply that by the height. That way we're reusing that function. Okay, so hopefully you can see what's going on here. The volume of a cylinder is the area of the circle times its height. So we may as well just call that function to do it for us. You can see the repeated code. Okay, so there you go. That's it. We've created, and let me run that again just to be sure that we're working correctly. See 12.1. So what's the radius of the cylinder? 10.2. And let's say it's 30.1. And there we go. Okay, so that's it. You can see how really straightforward it is. And the nice thing about this is when you read your code, you can see your main, and it's really easy to follow, right? Before in our main, we had all of this stuff in there. Now we're just saying area of the circle. Oh, okay. And remember, I can call these as many times as I want. In this case, it's going to ask me 2 times. I could put them in loops. I can do anything I want. So what's the radius of a circle? 10.1. Okay, it's asking me again, because I called it again. 10.2 this time. Then it goes to the radius of the cylinder. Okay, so that's it. That finishes off this video. You can see how easy it is to create these user-defined functions. And this is really what you want. You want your program to be modularized and have these small, well-defined units that do what you want it to do and just do one thing really, really well. In the previous video, I mentioned that the C++ compiler must know all about a function before it allows that function to be called. I didn't say why though. The reason for this is that the compiler can't check to see if the number of parameters passed in and their types are correct when the function is called, unless it knows about the function being called before it's called. There are 2 ways we can make this happen. The first way is to make sure we define all functions before they're used. This is okay for many small programs, but it quickly becomes very difficult to do. And in the case of 2 functions that call one another, it's impossible. So rather than have to worry about the order in which we define functions, C++ allows us to create function prototypes. Function prototypes tell the compiler all it needs to know about a function so that it can be sure that the function is being called correctly. Function prototypes are also called forward declarations, since you're basically telling the compiler, hey compiler, this is what this function is going to look like, make sure I use it that way. In smaller programs, all the function prototypes are generally placed near the top of a program, usually after the pound includes. As programs get larger, we split our programs up into multiple files, so we include .h or header files, and we include function prototypes in these files. We'll see that a little bit later in the course. Let's see what these function prototypes look like. Here I've defined a function called function name at the bottom of the slide. The function prototype for this function is the first line of code you see. Notice that it looks very much like the function header. That's the part of the function definition right before the body of the function. With a function prototype, the compiler doesn't need to know what the implementation of the function is, only its header information. So in this case, it knows that you'll later define a function named function name that expects no parameters and returns an integer. And if you use a function named function name, it will enforce those conditions. If you try to use it in any other way, say by calling it with an integer in the parameter list, then you'll get a compiler error. Pretty easy, right? You can have as many prototypes as you need, one per function, and it doesn't matter what order you declare them in. Let's take a look at another one. In this case, we have the same function named function name, but this time it expects exactly one parameter. So we provide a function prototype to the compiler that has an int in the parameter list. Note that we can supply the name of the parameter if we wish, but it isn't used by the compiler. The compiler doesn't care about the name, only the type. So either of these function prototypes can be used. Best practice is to provide the parameter names for documentation purposes. Let's see another example. In this example, we have a function that returns nothing when called. So the function prototype must include the void keyword prior to the function name, just like the function definition does. In this case, the function expects two parameters, an integer and a standard string. So either one of these function prototypes in the slide is valid. In one case, we provide the parameter types and names, and in the other, only the parameter types. The function prototype for the say hello function we saw in the previous video would look like this: void, say hello, and then the empty pressed. Notice the semicolon at the end. That's very important. We're not specifying a body, only the prototype. If we try to call this function in any other manner, we'll get a compiler error. So let's see how the compiler uses this information in the function prototype to help us write code. The function prototype here says that I'll define a function named sayHello that expects no parameters and returns nothing. Then I use or call the function in main. The first function call is fine since it matches the prototype. The second function call will cause a compiler error. We told the compiler that the function expects no parameters, but we're passing in an integer to the function call. The compiler won't allow this. The third function call is within an output statement. Think about this one for a second. You're telling the compiler to display the value that sayHello evaluates to. But the function prototype says that the function sayHello doesn't return anything. So the compiler gives you an error since something's not right. In this slide, I'm providing the same code that you saw in the previous video. However, in this example, I'm providing function prototypes for the sayHello and sayWorld functions at the top of the file. Now the compiler knows about these functions, and I can call them in any order I wish in my program, and the compiler will make sure that they're called as intended. Let's head over to the IDE and prototype some functions. Okay, I'm in the Code IDE, and I'm in the Section 11 workspace prototypes project. What I'm going to do here is I'm going to take the previous video where we calculated the area of a circle and the volume of a cylinder and so forth, and I'm going to rearrange these functions to actually break the program. Now this worked because I was very careful about how I defined these functions and where I defined these functions. So again, the compiler is going straight down and reading the source file. So it sees calc area defined here, calc area of a circle. Then it sees it used. Since it's already seen it defined, it's happy about that. In this case, it's the same thing. It sees calc volume of the cylinder. I use it down here. It's happy about that. So everything it's seen before it's being used. But if I take some of this code, let's say that I take all of this code actually, right before my main, and I just cut it, and I'm going to paste it after the main. Okay, so now we've got some issues because the compiler is now seeing, and let me clean up this white space a little bit. The compiler is now seeing area circle function being called, but it hasn't seen the definition yet because later. That's going to cause an issue. Same thing with volume of the cylinder. I'm going to get issues here. So let me run this, or compile it actually, it won't run. And there you go. Area of the circle was not declared in the scope. So it has no idea what that function's all about because it hasn't seen it yet. Okay. You're going to get two errors here. If we change the order and put this guy down here, we're going to get even more errors because now we're using something before it's being seen. So now we're going to get probably 3 errors, right? So that's a problem. How do we fix this problem? Well, that's where function prototypes come in. Okay. So let's use function prototypes. They're really, really easy to use. What I want to do is for every function that I'm defining, I want to prototype it before I've defined it. So obviously at the beginning of the file. And we'll do it right after the namespace statement. So let's look at this first one here. I'm just going to copy it and paste it because basically that's what I want. So I'm going to put it right here. And I'll just put a little comment here just so you know what's going on. So here are my function prototypes. Remember, the function prototype is only the name of the function and what it expects and what it returns with a semicolon at the end right here, no function body. So now the compiler sees that you've prototyped calc volume cylinder to expect 2 doubles and return a double, so it can type check that. Okay, let's deal with all of these. So let's do the next one, which is my calculate area of the circle. I'll copy it up here and paste it, semicolon on the end. Now remember, we don't need to have these variable names here, these parameter names. The compiler could care less, so I'm just going to get rid of this one just so you can see. The compiler doesn't care. All the compiler needs to know is what is the type of that parameter. So in this case, double is fine. As I mentioned earlier, best practice is to put the names in there for documentation purposes, but I'll leave it out here just so you can see that it actually does work just fine. Okay. So now we've got those two. Let's deal with area of the circle, and then we'll deal with volume of the cylinder. So we'll put area of the circle right here. The order in which you put the prototypes in doesn't matter because the compiler is going to see them all. So there's the area of the circle. Notice this returns nothing and expects nothing. Okay, and then we'll do the last one, which is the volume of the cylinder. So I'll come back up and I'll put that last prototype right in here. That's it. Now if I compile and run, I'll get a clean run. So we'll put 12 and type in whatever numbers you like. Okay. So that's pretty cool. Makes it really easy to not have to worry about order and, oh my goodness, you know, did I call this? Did I define this first? This was a problem in early languages. I remember using Pascal and there was just no way to get around this. Eventually they added something like forward declarations, which really makes things handy. So this is just standard practice that C and C++ programmers use to create those function prototypes. Now, what really is nice about this, suppose that I mess up my function prototype and I tell the compiler that that area circle function that I'm going to define later, this is the way you should check to make sure I use it correctly. Well, I'm not using it correctly right there because I'm not passing an integer into it. So this won't compile. This will give me an error right here. It says too few arguments to this function right here. So you've told it, again, remember, it hasn't seen this one down here yet, right? You've told it that that function will be used as in the prototype. And here you're not using it as in the prototype. Okay, so let me get rid of that. Also, if I send in, let's say a 5 into here, or a 4, right? Again, this is not going to match. You've just told it that this here expects nothing, but now you passed in an integer. So again, it's not going to like that. It's going to say too many arguments now to the function call. Okay, so let's clean that up. And that's really all there is to prototypes. Now, normally, as your programs get larger, these prototypes will end up going in a different file, in a .h file. And we'll get to .h files, or header files, our own header files, when we talk classes, because that's very common to create two pieces of the program. One is the header information, and one is the actual implementation. Very similar to what's going on here with IOStream. Those are really considered header files. So you're going to grab a lot of information from there. And that's usually where we put our function prototypes. But there you go. Let me run this again and make sure it's clean. Got a clean run here. So this I'll leave this code out there for you to play with as well. Get used to these function prototypes. We do them all the time, and it will really make your code better. Let the compiler help you every chance it gets. In this video, we'll learn more about function parameters, and we'll also talk about the return statement. When we call a function and pass data into that function, this data are the parameters to that function. In the function call, these data are called arguments. In the function definition, they're called parameters. We'll define the vocabulary more precisely in the next slide. As we've already seen, when we call a function, the arguments we use to call the function and the parameters that the function expects must match in number, order, and type. Let's see an example. In this example, we have a function prototype that tells the compiler that we'll define a function named addNumbers that expects 2 integers and returns an integer. Then in the main, I declare an integer variable named result, and we initialize it to 0. Then we call the addNumbers function and pass in the integer literals 100 and 200. The compiler will type check this function call to be sure it's valid. Since I'm passing in 2 integers and the function prototype says exactly that, then the compiler will not produce an error. You can see at the bottom of the slide that I've defined the add numbers function. It has two integer parameters, a and b. In the case of the function call in main, a will be 100 and b will be 200. 100 plus 200 is computed and 300 is returned. The 300 is then assigned to the variable result in the main function. Let's take a look at another example. In this example, I didn't provide a function prototype to save space, but you should know at this point that it would be void say hello Sanders string. Notice that the function say hello expects one parameter, and it's a C++ string object. And it displays hello followed by whatever string is in the name object. The next three statements would normally be in main or in another function. These are the function calls. The first is say hello Frank. Notice that Frank is a C-style string literal, but the function is ++ string object. Aren't these types different? Why doesn't the compiler produce an error here? Yes, the types are different, but the compiler will try to convert one type to another if it knows how to make the function call work. In this case, the C-style string literal Frank is converted to a C++ string object. The same would happen if a function expected a double and I passed an int into it. The int would be promoted to the double as we've already seen. Notice the last function call. In this case, I'm calling the function sayHello with a single string object parameter myDog, which is a variable name for a string object with the string Buster in it. Let's talk a bit about how parameters are passed into functions. In C++, when you pass data into a function, that data is passed by value. What this means is that the value of the data is passed in by copy, so the compiler makes a copy of the data. That means that the code in the function does not change the argument that was passed in. When we finish the function, the original data that was in the function call will be unchanged. This is good and not so good. It's good because since we're making a copy, we can't change the original argument by mistake or intentionally. It's not good because sometimes making a copy of data can be expensive, both in storage needed and in time needed to actually copy that data. Also, sometimes we really do want to change the actual data being passed in. Fear not, C++ has solutions for all these use cases, and we'll learn about them soon. Let's define some vocabulary used in programming languages, that is, formal versus actual parameters. Formal parameters are the parameters defined in the function's definition, in the function header. Actual parameters are the parameters that are used when the function is called, that is, in the function call statement. Many programmers and languages call actual parameters the arguments to a function. In C++, the actual parameters are passed by value or copied to the formal parameters. Let me show you an example that will make this clear. In this slide, I have a function definition for a function called paramTest, and this function expects one parameter called formal. This is an example of a formal parameter. If this function expected more than one parameter, they would all be considered formal parameters. In the main function, I'm declaring an integer named actual and initializing it to 50. I'm displaying actual, which will display 50. Then I'm calling the paramTest function with the actual parameter. This is the function call. Any parameters passed to functions here are considered actual parameters. In this case, the value of the actual parameter is copied to the formal parameter. So formal in the paramTest function will have the value 50, but it's at a different location in memory than the actual since a copy was made. I then display formal in paramTest, so 50 is displayed. Then I assign 100 to formal and display it again, so you see 100 is displayed. Now the function is done and we return back to main and we print actual. Actual will still be 50. It was never changed because paramTest was working with a copy all along. It's very important that you understand the concept of pass by value since it's critical to understanding functions. Let's talk about the function return statement next. As we've already seen, if a function is defined as returning a value of a specific type, then the function must return a value of that type using a return statement. We've already seen a few examples of this, and we've been doing it in the main function all along. If the function return type is void, then the return statement is optional. A return statement can occur anywhere in the function body, but you usually see it as the last statement in the function body. The return statement immediately terminates the function. It's possible to have multiple return statements in a function depending on the logic in your code. However, this is not a best practice. You typically want a single return statement. Remember having multiple break statements in a loop and the potential problems you could have with readability? Well, the same is true with multiple return statements and functions. Finally, if the function returns a value, then this value becomes the result of the code that's called the function. Let's head over to the IDE and see some examples of parameter passing and pass by value. Okay, I'm in the IDE and I'm in the Section 11 workspace in the Function Parameters project. In this example, what I'd like to do is go over some simple function calls that pass in parameters by value. And I want to make the point, and hopefully you'll understand that those by value parameters do not change. And that's really important to understand. So I've got 4 function prototypes here. The first one is called pass by value 1. The second is called pass by value 2. And the first one just expects an integer. The second one expects a C++ string object. The pass by value 3 function expects a vector of string objects. And the last one, print vector, just prints out a vector. So if you send it a vector of strings, it displays all the strings in the vector. Okay, so let's look at it, the first one, pass by value 1. It expects a number, and the parameter name for that number is num. That's the formal parameter. And all I'm doing is changing num to 1,000. Really, really simple. So let's look at my main. In my main, I've got num, which is 10, and I'm simply saying num before calling pass by value 1 is, hopefully that'll print out a 10, right? That's what we expect. Then I'm going to call pass by value, and I'm going to pass into it num, which is 10. Remember, pass by value 1 changes that value to 1,000. And then I come back and I print out that number again. Now, you may think that we're going to get 1,000 here, but we're not. It's passed by value. So we actually passed in a copy to that function. So the function was changing the copy, not the actual, which is this num here. So let me run this, and then I'll walk you through exactly what's going on. You can see here, num before calling, 10. Num after calling, still 10. Okay, so let's talk about that. Remember, num is equal to 10, and it's in my main. So in this case, here's my main function. And it's got a local variable in there called num, and we initialized it to 10. Then we called this function right here. So this would be pass by value 1. And I'll just call it 1, okay, just to save some writing time. So that's pass by value 1, and it expects an integer, num. So it's got its own copy of num. That's the formal parameter. And at this point, the 10 gets copied over to num. Okay? Now I'm going to set num to 1,000. Remember, this num right here refers to that guy, not this one. So I'm changing the local num, the formal parameter, to 1,000. So I'm just changing this one to 1,000. I never touched this one. Now this function is finished. So this function is now finished. This is gone, and I'll talk about what gone means in a couple of videos when I talk about activation records and the stack. That's it. Now we return. And in the main, we display num. Well, num never changed. Remember, this was an absolute copy of it. Okay, so hopefully that makes sense with pass by value. Let me show you another example. Here we've got another num, which is 20. So don't get confused with the names. I could use any name I want in that formal parameter. I just chose num to make a point. In this case, it's another num. So when we print here, we're going to print a 20. Then we're going to call pass by value 1 again and pass in that num. So the 20 gets copied to the formal parameter. We change it to 1,000. Again, we change that local copy. And when we come back, we still have a 20, right? We never touched the actual. So let me run this. And now we're going to see 1010 and 2020, just what we expect. Okay. It's no different when you use objects. So in this case, I'll uncomment that code. In this case, you can see that I've got a string, a C++ string object called name, and I've initialized it to Frank. And then before I call pass by value 2, I'm going to display it. That's going to display Frank. Then I'm going to pass that string object into pass by value 2, which is another function. And that function is right here. It's going to change its parameter to changed. Whatever was there before is now changed. And then when I come back, I'm printing out name again. Name has not changed because that changed here changed a copy. Okay, so let's walk through this one again. So what do we have? We have main. We've got the main function, and it's got a variable called name, and it's Frank. Okay, then we called pass by value 2. So this would be pass by value 2, and it has a parameter, right? A formal parameter, which is a variable. It's called S. And we copied Frank in there. So right now this becomes Frank. Now we say S is changed. So we get rid of Frank and we replaced it with changed. And again, these are all strings, string objects. Now we return back to main. This function is now done. I never changed the name because I never even knew about it. I was working with a local copy all along. Okay, so it's same thing with integers as with objects. So in this case, if I run this program, you can see the name before calling pass by value 2 is Frank, and the name after calling pass by value 2 is Frank. Again, it hasn't changed. All right, let's do one more just to drive this point home. This is really important that you understand what's going on here. In this example, I'm using a vector of string objects. I don't think we've used a vector of string objects. We basically used, I think, vectors of integers and doubles. We can have a vector of anything. So here we're saying that Stooges is a vector of strings, and the strings in that vector are Larry, Moe, and Curly. So I'm printing out Stooges before calling pass by value 3, and I'm calling this function called print vector that just prints out those strings in that vector, whatever they happen to be. Then I'm calling pass by value 3, and I'm passing in Stooges, and then I'm just printing it out again. Okay, so let me run this first, and then we'll walk through it. So you can see that before calling the function, Larry, Moe, and Curly, after calling, that should say after right there, after calling the function, Larry, Moe, and Curly. Okay, so let me change that, make that correct. That way when you guys see it in the resources, you'll know what I'm talking about. So let me run that again. Okay, so before calling, Larry, Moe, Curly, after calling, Larry, Moe, Curly. So let's walk through this example. Here is the function pass by value 3. So in this case, what have I got? Well, I've got my main, and my main has the Stooges variable, which is a vector of strings. In this case, it's Larry, Moe, and Curly. Right? These are all string objects. Right? Now, I call this function right here, and I pass in Stooges to it. So this is pass by value 3, and it has that formal parameter v. That could be any name we want. Right now, Larry, Moe, and Curly get copied into v. So this will be Larry, Moe, and Curly. Now I execute this line right here, v.clear. That deletes these guys. So now v is empty. And that's it. Then I return back to main. What happens? This function is now gone. And when I come back to main, it still has that Stooges vector, Larry, Moe, and Curly. I never touched it because, again, I was working with a copy. In the next few videos, we'll learn how to send information in so that I can modify the actual parameters. But it's important to understand that by default, this is the behavior, pass by value, make a copy. Okay, so hopefully that makes sense. And if there are any questions, please post them on the course forums. In this video, we'll learn how we can call C++ functions using default argument values. As we've seen, when we call a function, we must provide all the arguments that that function requires, and they must be in the right order and of the right type. But sometimes when we call functions, some of the argument values that we pass in tend to be the same values most of the time. For example, if we have a function that calculates the cost of an item, we can provide the function with the base cost of the item and the sales tax rate. Suppose that 98% of our customers live in a region where the tax rate is 6%. That means that we have to provide the tax rate in every function call, even though it will almost always be 6%. C++ allows us to provide default values for arguments. So in the case of the sales tax, if we omit the argument from the function call, then the C++ compiler will automatically replace it with the default value of 6%. However, if we have a customer whose sales tax rate is 8%, then we can provide it explicitly and override the default value. As we'll see in the next few slides, we can add default arguments to the function prototype or the function definition, but not both. But best practice is to do it in the function prototype. Default arguments must appear at the tail end of the parameter list. We can also have multiple default arguments. Let's see an example that demonstrates default arguments. In this example, we have a function with no default arguments. In the next slide, we'll modify it so it does have a default argument. The function is called calculateCost, and it expects the base cost of an item and the tax rate. The function calculates the tax amount and adds that to the base cost and returns that value to the caller. In the main function, we're calling the function with 100.0 as the base cost and 0.06 or 6% as the tax rate. In this case, 106.0 is returned from the function and assigned to cost. That's pretty easy. But if 98% of our customers will have a 6% tax rate, I'm forced to supply this every time I call the function. Why not let the compiler default the tax rate to 6% unless I tell it otherwise? Let's do that in the next slide. Here we have the same function, except that the function prototype has been modified to provide a default value for the tax rate. Notice that the parameter tax rate in the function prototype now has a default initialization to 0.06 added to it. This effectively tells the compiler that if this argument is not provided by the function call, then use the value 0.06 for tax rate. Simple as that. Now notice the two calls in the main function. The first call simply calls calccost with 200.0, which is the base cost. Since the argument for tax rate is not provided, the compiler will use 6% for the tax rate. In the second call, we are providing the tax rate. In this case, the compiler will use that and ignore the default value. This can be pretty handy. Suppose we have a function that prints documents and we have to supply the document name, the printer to print to, the paper size, the resolution, and so forth. Again, most of the time we print to the default printer with default settings, but sometimes we need higher resolution or a different printer. You get the idea. In this case, we can provide multiple default parameters for everything except the document name, which is always required. This makes writing the code much simpler. Let's add another default parameter to the calccost function. In this example, we'll calculate the cost of an item based on the base cost of the item, the sales tax, and a shipping charge. As before, most of the times the sales tax will be 6%, and in this example, the standard typical shipping charge is $3.50. So, most customers will have a 6% tax rate and a $3.50 shipping charge. We can easily add a second default argument to this function. Notice that in the function prototype, we added another parameter named shipping, and we default this value to $3.50. The function body now calculates the tax for the item, adds the shipping charge, adds this to the original cost of the item, and returns the result to the caller. In the main function, we're calling calccost in three different ways. In the first call, we're providing all three arguments to the function. In this case, no default values will be used, and the tax rate will be 8%, and shipping will be $4.25. In the second call, we're providing the cost of the item and the tax rate of 8%. In this case, the default value for shipping will be used, but the tax rate will use the 8% we provided. In the final example, we're only providing the cost of the item. So in this case, both default values are used. The tax rate will default to 6% and the shipping charge to $3.50. As you can see, default argument values give us the ability to make our code less verbose and potentially prevent errors by using default values rather than having to supply all of the arguments to the function all the time. In the next video, we'll learn about function overloading. Before we talk about function overloading in the next video, let me go over default arguments. I'm in the Section 11 workspace in the Default Arguments project, and this is the same example you saw on the slides. Here I've got a function called calculateCost that expects three doubles: the base cost, a tax rate, which is a default argument at 0.06 or 6%, and a default shipping, which is $3.50. Now, if those arguments are not supplied, then the defaults kick in. It's really pretty simple. And here's the calculation. Notice I don't have to include the function default arguments here in the function definition, only in the function prototype, and that's usually where you see them. So the code here says base cost plus equals base cost times the tax rate, so I'm figuring out what's my tax, and I'm adding the shipping to that, and then I'm adding the whole thing to base cost. So I'm not taxing the shipping. And then we've got some sample calls. In this first example, I'm calling calculate cost with all three arguments. So in this case, none of the defaults will be used. I'll use 100 for the base cost, I'll use 8% for the tax rate, and I'll use $4.25 for the shipping charge. I expect to get back $112.25. Okay. For this example here, I'm providing the first two arguments, and I'm not providing the shipping. So in this case, it's going to use 100 as the base cost, 8% for the tax rate, and it'll default to $350 here for the shipping. And in this last example, I'm supplying the base cost only. So in this case, 6% and $3.50 are what are going to be used. So if I run this program, you'll see that our results are exactly as we expected. 112.25, 111.50, and 215.50. Okay. So you can see default arguments are pretty easy to use. I could also default the base cost if I wanted to. I could say that the base cost is 100. Maybe that's the typical item that most people order. So in this case, I could just simply say cost is calc cost, right? With nothing in the parentheses. So I'm not supplying any arguments here. That's it. So what's going to happen here is it's going to use all three default arguments. So let me print that out real quick. So in this case, we expect the same result as well, if we would have done 106. So we'd have 100 is the base cost that's being used by default. We're using a 6% tax rate, so that's another $6. And our shipping would be $350. So in this case, we expect $109.50. So let's give that a shot. And that's what we're getting here, $109.50. This is pretty straightforward. The only rule with default arguments is that once you create a parameter that has a default value, then you've got to default the rest of them. So in other words, I can't say that base cost is 100 and then not have one here, because that's going to give me an error, right? Once you start, they all have to be on the tail end. So in this case, I could just say 0.06. So that's really the only rule there. And I'll run that again just to make sure I've got no errors, and there you go. So let's add another default type function to this application. How about a greeting function? So let's do something like this. Let's create a function prototype here for a function called greeting that expects a string, which is someone's name. Now let me include string because I need the library. So that's a string name. Perfect. So that would be Frank, Metropolis, Joe Miller, whatever you want. Then I've got another string, which is the prefix that we want in front of their name, Mr., Dr., Mrs., whatever you like. And I'm going to prefix it to Mr. Let's say that most of my customers are male. And I also want a suffix. And in this case, the suffix, I'm going to default it to just the empty string. Okay, so that's my function prototype. Let's implement this function now. We'll implement it right down here. And at this point, we don't need those default arguments. We can just get rid of them from here, and it cleans up the code a little bit. All right, so what do we want to do here? We just really want to display some stuff, right? So let's just say I want an output statement, and I'm going to say hello, followed by a space, followed by the prefix. And what we could do here is we could append a space. Right, we can use concatenation here, and the name, and another space, and the suffix. Okay, so we're just using concatenation here, just like we've learned in string class. And then we'll use the end line to finish it off. Okay, so let's run that and give it a few example runs here. So let's say, how about, let's do a really simple one. How about greeting? And I'm going to supply all of these arguments. So I'm going to say Glenn Jones is the name. Okay. The prefix will be doctor, and the suffix will be MD. Okay, so if we run that, we expect this to display Dr. Glenn Jones, MD. Okay, so let's give it a shot. And I forgot the semicolon. I'll fix that real quick. And there you go. Hello, Dr. Glenn Jones, MD. Perfect. Now let's run some of the other examples. So how about we do something like greeting James Rogers. How about professor and PhD for the suffix? Okay, we'll run that. And now we'll say, hello, Professor James Rogers, PhD. Pretty easy. Now let's use some defaults. In this case, we'll say greeting. Let's say Frank Miller and doctor. No suffix in this case, so it'll default to the blank or the empty space. So in this case, it'll just say Dr. Frank Miller, which is what I want. And then let's do one more. And we'll just say greeting. Let's say William Smith. So in this case, it's going to use all the default values. So it's going to use Mr. William Smith followed by the empty string right there for the suffix. Okay. So in this case, we're just going to see Mr. William Smith. There you go. Okay. If we have Mary Howard, and she would be Mrs. And we can give her a title as well. Whatever we like. There you go. So now we've got Mrs. Mary Howard, PhD, instead of doctor. We could have said doctor here as well. You can see all the different combinations. This can come in pretty handy. I used to work with someone who used to say that if something is always required, then it should never be required, which makes a lot of sense. And I think that's part of the idea behind using default arguments and using overloading, which we'll talk about next. In this video, we'll learn about function overloading. In C++, we can have functions with different parameter lists that have the same name. For example, I may have many ways to display information to the screen depending on what I want to display. So rather than having many functions with different names, such as display char, display int, display double, and so forth, we can have a single name display, and then implement a version of the function for each type of parameter. Then we just let the compiler figure out which function to use based on the function call arguments and the defined function parameters. It sounds more complicated than it is, and we'll see an example in the next slide that'll show you just how simple it is. This is a great use of abstraction, since as a developer, all I need to think is display and pass in whatever information I need. I don't have to keep track of dozens of different function names. In software engineering, we have a principle called polymorphism, which means many forms for the same concept. This is an example of polymorphism. Let's see what overloaded functions look like. In this example, we have two functions that are both called add numbers. The first function expects two integers, and the second function expects two doubles. I'm only showing the function prototypes in this slide, but we actually have to implement both functions. I'll do that in the next slide. Notice that in main, I'm calling both functions, but I don't have to think about different names. I just want to add two numbers. If I call add numbers with two integers, then the int version of the function is called. If I call add numbers with two doubles, then the double version of the function is called. In this slide, I'm providing the function definitions for the add numbers functions that we prototyped in the previous slide. It's important to understand that we must implement all of the overloaded versions. Notice that the code for these two functions is nearly identical except for the types. C++ has a feature called function templates that allow us to just write one generic version of the add numbers function, and it will take care of providing the correct version when called. Function templates are a little bit more advanced topic, and we'll discuss it when we talk about the standard template library. Let's take a look at another example. In this example, I'll only show the function prototypes, but remember that you'd have to implement all of these. I have 5 functions named display. The parameter lists for these functions must be different so the compiler can tell them apart. Once these functions are implemented, I can call display and pass in my data. The compiler will check the type of the argument in the function and match it to one of the available overloaded display functions. If it can't match it, or if it can't convert the argument to one that matches, then we get a compiler error. There is one restriction to function overloading. the return type is not considered when the compiler is trying to determine which function to call. So here we have two overloaded functions, both called getValue, and both expect no parameters. The only difference is that one returns an integer and the other a double. This will produce a compiler error, since the only difference is the return type. Consider the output statement at the bottom of the slide. Which function would the compiler call? It could call either, and that's the problem. It won't guess, so it'll produce a compiler error. Overloading functions is used extensively in object-oriented design, and we'll see it again when we design our own C++ object-oriented classes. I'm in the CodeLight IDE in the Section 11 workspace, and I'm in the Function Overloading project. Here I just want to go through some examples of overloading a function. Remember, overloading a function simply means using the same name for various forms of that same function. In this case, it's print. And what I want to do is I want to overload print to work with different types. So you can see some of the function prototypes here. In this case, I've got an int version of print. So if I pass in an integer to print, it'll use this version of the function, one that expects a double, one that expects a C++ string object, one that expects two C++ string objects, and the last one expects a vector of string objects. Okay? Remember, we have to implement each one of these, and that's what I'm doing here. I'm just saying printing int, printing double, so that we know which one's being called. So in the case of print int, it simply says printing integer and it displays the number. For double, it's doing the same thing, string, and so forth. Okay? And then for the vector version, it's just iterating through the vector and printing out all the strings in the vector. So let's see how this works. In this first case, I'm simply calling print and I'm passing in 100. Now 100 is an integer, so I expect that this integer version of print is the one that's going to be called, and it'll say printing int. Okay, so let's give that a try. Printing int wanted. In this version, I'm passing in a character. Now, characters are always promoted to integers. So in this case, it's going to call the same function, the one that expects an integer, but it's not going to print out the character A. It's going to print out 65, which is the ASCII code for A. Remember, it's using integers here. So let's run that. And there you see it says printing integer, and it's printing the 65. In this case, I'll comment both of these out. In this case, we're going to use the double version, which is this version right up here. Print expecting a double, and it's just going to say printing double and display the number that was passed in. So in the first example, I'm passing in 123.5. No problem, 123.5 is a double, so that should match perfectly. However, in the second example, that F right there makes this a float, not a double. So in this case, I'm passing a float to the function, but there is no overloaded function that expects a float. So what the compiler does is it will promote the float to a double. It'll match that function and call it. So both these statements will use that same function. Okay, let's run that. And you can see here 123.5, and in this case 123.3. Okay, so what about C-style strings? Let me uncomment that out. And remember, we've got a version of print right here that expects a string object, and it simply prints out that string object. However, I'm not passing in a string object here. I'm passing in a C-style string, an array of characters. That does not match that function prototype. But the C++ compiler knows how to convert a C-style string, right, an array of characters, to a C++ string object. So it will use that conversion, and it'll pass in the literal, make it an object, and then we're going to display the object. So if we run it, you'll see printing string, C-style string. Okay, exactly what we expect. Once you understand how the conversions work, it all makes a lot of sense. In this next example, I'm declaring right here S to be a string object. This is not a C-style string. This is a C++ style string object. And I'm passing it into print. That's going to match exactly, and it'll print out C++ string. All right, in this print statement here, we're passing in a C-style string and a string object. Okay, both. Now we've got a version of a print function right here that objects. Well, no problem, right? We'll convert the first argument to a string object and then pass the second one as well. So in this case, when I run it, you'll see that that same printing two strings method is called with a C-style string and a C++ string. Okay, pretty cool. And then the last one is this vector. Here I'm creating a vector called Three Stooges, which is a vector of string objects, and we've got Larry, Moe, and Curly in there. And I'm calling the print function and passing in Three Stooges. So it's going to match this one right here that expects a vector of strings. And I'm just going to iterate through there and print out the Three Stooges name. So the three strings in that particular vector. Okay, so I'll run it. And there you go, printing vector of strings, Larry, Moe, and Curly. So you can see how nice it is to be able to overload functions. The nice part about it isn't so much all the code that I've written. That's not that great. The nice part about it is once the code is written, I can just think print. So if I'm solving an application, I'm printing, print. I'm printing everywhere. I'm not doing, I don't have to do print int and print string and so forth. I'm just thinking print, which is what abstraction is all about. Now, there's some couple of things you need to worry about when you're overloading functions. Be careful when you overload functions and you use default arguments. Okay, I'll show you why. Here's an example of the print with the integer version. I could certainly default this to 100, let's say. So if I don't supply the argument to the print function, it's going to default to 100. And let's test that out. We'll do it right up here. Okay, so at this point now, we should get 100 here and then 100 on the next line as well, right? So let's run that, and you can see there's the 100. That's the default argument right there. That makes sense. But what about if we didn't do that, and we did it down here in the print double? Let's say that we want to default this one to 125.5. Now, when I call print here, it will default to 125.5 because it's up here, right there. That's the one that's going to match, right? So there's the 125.5 and the double version gets called. Again, it makes sense. Where you run into trouble is when you do both. Let's say you do something like that. Now you're really in trouble because the compiler can't figure out which one to use. Again, look at the print call right here. It says print, but it doesn't supply any type information. So now the compiler can choose either one because they both match. And it's not going to choose either. It's going to give you a compiler error. And when I run it, it'll say something about an ambiguous call right here. Error, call of overloaded print is ambiguous. So whenever you use overloaded functions with default arguments, you've got to be a little careful. So let me get rid of that, and I'll set those back up to the way they were. Okay, so that covers overloaded functions. We're going to see overloaded functions a lot when we talk about object orientation, and when we create our own classes. We want to have different ways to initialize our classes. You saw that with the vector class and the string class, all the different ways that we can create those objects. Well, that's all based on overloading functions. In this video, we'll learn about passing arrays to C++ functions. We can pass arrays into functions by providing the square brackets in the parameter information. So in this case, we can have a function named printArray that expects an array of integers and returns nothing. The idea is that this function iterates through the array and displays the array values. Pretty handy function, right? But arrays are different in C++. Remember that an array name evaluates to the address or location in memory of the first element of the array. In other words, the beginning of the array. So what's being passed into the function is not a copy of the entire array, but only the address of the first element of the array. That means that the function has no idea how many elements are in the array. So the programmer doesn't know how many times to iterate. So when we pass arrays to functions, we also need to pass in the size of the array so that we now know how many times to iterate. Let me show you an example. In this example, you can see that both the function prototype and the function definition have square brackets after the formal parameter name. This tells the compiler that the function expects an array of integers in this case. So far, so good. Then in main, I have an array of 5 integers called myNumbers, and it's been initialized to the integers 1 through 5. So I call the printArray function and pass in the array myNumbers. All good so far. Now I execute printArray function, but I have no idea how many times I need to iterate. Since the array name has no size information, I'm stuck. If the array has a sentinel value, like a C-style string, then I can iterate until I see that sentinel value. But in this case, the myNumbers array has no such sentinel value. There's no way I can write this function body in a way that it will work with any array of integers. So the solution is to pass in the size of the array to the function as well. Let's do that next. Now we've added a size parameter to both the function prototype and the function definition. In the main, when I call the function, I pass in my numbers and the size of the array, which is 5 in this case. Now when I execute the body of the printArray function, I know the location of the array, which is the array name, and I know how many elements are in the array. I can easily write a for loop now that iterates through the array and displays every integer. This looks great, but there is one potential gotcha that you need to be aware of. Since we're passing into the function the location of the actual array that was declared in main, that means that we can modify that actual array from within the function. This could be useful in the case of a function like zeroArray that we can call whenever we want to zero out all the elements in an array. However, in the printArray function, we don't want to modify the array. If we do, it's probably an unintentional error. We'll see how to protect ourselves from this kind of error in the next slide. But first, let's see how we could write a useful function like zeroArray. In this case, the zeroArray function receives the location of the array and the size of the array. We could simply iterate through the array and set each array element to 0. Notice that when we print the array in main after we call zeroArray, all the array elements are now 0. So let's get back to see what we can do to have the compiler help us so we don't change an array we don't want to. We can define function parameters as const parameters. This tells the compiler that these parameters are read-only within the function body. Any attempt to modify them will result in a compiler error. So in this case, notice that we included the const keyword right before the array parameter declaration. That's it. Now if I try to modify any array element, as I do in the assignment statement, a compiler error will occur. Depending on your compiler, the error message will say something like error trying to assign to a read-only value. The idea of passing the location of a variable to a function instead of the value of a variable is fundamental in understanding the next topic we'll talk about. It's called pass by reference. Before we talk about pass by reference, I want to be sure that you really understand the whole idea of passing arrays to functions. So I'm in the IDE and I'm in the section 11 workspace, the Arrays and Functions project. And let me show you what I've got here. Let's start at the main. I've got a real simple array here, array of integers called my scores, and I've initialized it to 198, 90, 86, and 84, right? 5 integers. Now what I want to do is I want to call a function called printArray, and I want to pass into that function the array and the size of the array, as we saw before. Perfect. That should print out 198, 90, 86, and 84. Now I've got a function called setArray. And what this function will do is it'll set every value of that array to 100. So when I come back, it'll print out 105 times. So that will actually modify the array. So let's see what these functions look like. They're pretty straightforward. There are the function prototypes. That's the function prototype for printArray. It expects an array of integers and the size of the array. The setArray function expects an array of integers, the size of the array, and the value that we want to set each one of those elements to. All right. So let's look at the printArray. And I put const here because it's something that we need to think about whenever we write functions that work with arrays. So let's look at this. What do we do here? Well, we iterate. We iterate for I equal to 0 while I is less than size. That's the idiom that we do all the time when we're working with arrays. And we're incrementing by 1. And then all I'm doing is I'm outputting array sub I. So I'm going to go from array sub 0, array sub 1, array sub 2, all the way to array sub 4 in this case. And I'm going to print out each one of those integers. Then I'm just going to print a new line at the end. That will print out 100, 98, 90, 86, and 84. Perfect. So that's that line right here. Then I'm going to call setArray. And I'm going to pass in, again, the array, the 5, which is the size, and 100. In this case, rather than doing any outputting, what I want to do is I want to loop through again. So the same loop from I equals 0, I less than size by 1. What I want to do at each iteration of the loop is I want to set ARR sub I, right? The ith element of that array to the value that was passed in. So in this case, I'm modifying all 5 of the array integers to 100. Then I'm printing it again. So what I expect from this program is the first print array statement is going to print 198, 90, 86, and 84. Then the last print array statement here is going to print 5 100s. Okay, so let's run this and then we'll walk through this in detail so you can see exactly what's going on. There you go, 100, 98, 90, 86, 84, and then 500s, exactly what we expected. So let's walk through this. Let's start with the printArray function first. And my main has that array right here called my scores. And I'm going to draw this visually so you can see exactly what's going on. There's my scores. It's an array of 5 integers. Okay, and I'll put them in here: 100, 98, 90, 86, and 84. The value of the name of an array is the location of that first element in the array. So let's say that that integer 100 here is at location 2000. And I'm just making that up. It could be any location. But that's 2000. So whenever the C++ compiler sees an array name, this is what it's going at. In this case, my scores will evaluate to 2000. Okay, perfect. So now I'm going to call print array right here. This is what's going on. So now I'm in my print array function. And print array has several local variables. It's got array, it's got size, and it's got this I right there. Let's just worry about the array and the size variables right now. So there's my ARR, I'll just call it array, and here's my size. When the function is called, the values are copied. So my scores is 2000. It's not the entire array. It's 2000. So 2000 gets copied over here. Size is the 5. So size gets the 5. Right. Now I start looping. And the first thing I do is it says, basically I is 0, right? So what I'm going to do is I'm going to see out ARR sub 0. Well, what does that mean? That means the first integer in the array. Well, where's the array? Right here. That's that guy right there. So you can see that this print array function is referring to the actual array in main because the array was never copied. Instead, the address of the array was passed in. It's going to go through each one of these through the loop. It's going to print out ARR sub 1, which is that guy right there, 98. So it's going to display them all. Okay, that makes sense? I hope so. So again, this will print out right here. It'll display 100, 98, just like we saw, 90, 86, and 84. Now let's look at this function call right here. I still have my scores array, and it's still the same. I haven't changed it. And let me put those numbers back in here. I'll put 100 in here, 98, 90, 86, and 84. Right. Now I call set array. Well, set array is over here. And it's got the same idea, right? It's got the ARR variable, the size, and the value. So it's got ARR, it's got size, and it's got value. Let's again assume that this is address 2000 right here. That's that name. So in this case, I'm passing in the 2000, I'm passing in 5 for size, and I'm passing in the 100 for the value. And then I'm looping. And notice that loop. Every time in the loop, this is what I'm doing right here. So the first time through, I'm saying ARR sub 0 is value, which is 100. It's always going to be 100. Well, where is ARR sub 0? It's at 2000. So what I just did was I just came in here and put 100 in here. Then I'm going to increment I, and it becomes ARR sub 1 equals 100. So this guy is over here. I just got rid of that one. And what I'm doing is I'm initializing the entire array to whatever value was passed in, which is 100 in this case. Right? When this function is finished, it's gone. And what I'm left with is the updated array. So this will print out 5 100s as you saw. Okay, so hopefully that makes sense. It's a real different from pass by value. But when you think about it, it is still doing pass by value because it's copying the value of 2000, right? It's not copying the entire array, but it's copying 2000, which is what my scores defaults to. That's its value. All right, so one last thing. We really don't want to be able to change that array in the print array. Okay. Let's say that we did something like this. Something really silly. We could say ARR sub 0 is 10,000. Or you know what? Let's do 50,000 just so we can really see the difference. Okay. This is probably a bug. Okay. Print functions don't tend to change anything. They just display information. But let's just say that we've got some bug in our code. Now, right here, I'll call print array again. and I'll call it exactly the same with my scores and 5. So look what happened here. I called print array here. It printed out the 500s, but then it changed one of them, the first one, to 50,000. And then I'm calling it again. So I'm expecting to see that first, there it is. You see it? That first array element right there just got changed to 50,000. How do I prevent that? A real easy way to prevent that is to come up to your print array function right here and say that this is a constant array. And I can do the same thing in the definition. Now if you try to compile this, there's the error. Assignment of read-only location ARR. So in other words, this function now, print array, cannot change array. That's really what we want. So we can comment that out, and now we'll run just fine. Okay, notice that's exactly what we want. So when you're writing functions and they're passing around objects, especially arrays and vectors and things like that, especially when we talk about pass by reference in the next section, you've got to be really aware of what can change what. And if you do have access to the actual and you don't want to change it, const is the way to go. Okay, and we'll talk more about that when we talk about pass by reference. So far, we've seen that when we pass a parameter into a function, the default is pass by value. That means a copy of the actual parameter is made. We also saw that when we pass an array into a function, we don't make a copy. Instead, we use the location of the array, which means we can change it from within the function. Well, sometimes we want to be able to change an actual parameter from within a function. As we saw with arrays, this is achieved by passing in the location of the actual parameter. We can do this in C++ for any variable type, not just arrays, by using reference parameters. Reference parameters create an alias, so now the formal parameter in the function is an alias to the actual parameter. No copy is made. When you change the formal parameter, you're changing the actual parameter. This is called pass by reference, and it's really easy to achieve in C++ by using the ampersand symbol in the parameter list. Let's see an example. In this example, we have a function named scaleNumber. Notice that the parameter list to the function is not an int named num. It's a reference to an int named num. That's what the ampersand does. So now when we use num in the function body, we're referencing the actual parameter. Let's walk through this. In main, we declare an integer number and initialize it to 1000. Then we call the scaleNumber function and pass in the actual parameter number. We now transfer control to the scaleNumber function. Since the formal parameter in the scaleNumber function is a reference parameter, this means that num is an alias for number. If we change num, we're changing number. Behind the scenes, the location of number is being passed into the function. So the code in scaleNumber checks to see if the number is greater than 100. In this case, it is. It's 1000. So we set num to 100, and the function completes. When we return to main and display number, it will display 100. Pass by reference can be super useful for several reasons. First, it allows us to change an actual parameter if we need to. Second, we don't make a copy of the parameter, which could be large and take time. But we have to be aware of potentially unwanted changes. Let's see how we could swap two numbers using pass by reference. In this example, we're writing a function that swaps the values of the two integers passed into it. Take a look at main. X is 10 and Y is 20. X and Y are first displayed and we get 10, 20, just as we expect. Then we call swap and pass in X, Y. Then we display X and Y again. Now they're 20 and 10. We swap them. Look at the function definition and notice that both A and B are reference parameters. So when I call this function with X and Y, A and B become aliases to X and Y respectively. In the body of the function, I set temp to A, then A to B, and then B to temp. And we've swapped the two values that were passed into us. What do you think would happen if we didn't use pass by reference and we used pass by value? Well, the actuals would be copied, so we would swap the copies in the function and then return. When we get back to main, the actuals haven't changed since we were working with copies. Let's talk a bit about how parameters are passed into functions. Let's see what happens when we pass in a vector object to a function. In this case, I have a function called print, and it expects a vector of integers. Notice that in this case, we're using pass by value. Inside the print function, I simply use a range-based for loop and display the vector elements. Pretty easy. But there's one issue with this code. That is, we're using pass by value. So we're making a complete copy of the vector object in the function. So the formal parameter v will be a copy of the actual parameter data in this case. In order to make a copy, we need to allocate storage and copy values over. If the vector is very large, we could run into performance and storage issues. So why don't we use pass by reference instead, so we can avoid the copy? Let's do it. Notice that now I'm using pass by reference since I've declared the formal parameter v as a reference parameter using the ampersand. The output of this program is exactly the same as before, but we avoid the storage and copy overhead of pass by value. But there is one issue. Since I'm using pass by reference, the print function could change the value of the vector. It could even erase the entire vector. This is probably not a good idea. So let's tell the compiler that this is a constant reference. So now I've added the const keyword to the parameter. Now I've told the compiler to use pass by constant reference. So if I try to make any changes to the formal parameter v in the function, I will get a compiler error. This is really the best of both worlds, since we're more efficiently passing information to the function, but we're still ensuring that the function can't change the data by mistake. Let's head over to the IDE and see this in action. Okay, so now I'm in the IDE and I'm in the Section 11 workspace in the Pass by Reference project. This is the same project that we used when we did pass by value. The only thing I've changed is I've made the parameters reference parameters now. So you can see the way I did that was just by including that ampersand. Now these are the same function prototypes. I've just named the functions pass by ref1 rather than pass by value as we had before. Okay, so I've got 3 pass by reference functions and just a simple print vector function that displays a vector element by element. Pass by reference 1 expects a reference to an integer. Pass by reference 2, a reference to a string. Pass by reference 3, a reference to a vector. And then the print vector function expects a reference to a constant vector because I don't want to be able to change the vector from the print function. Now, I've implemented all of these functions and basically the code hasn't changed from before. I set number to 1,000, I set the string to changed, and I clear all the elements out of there. Now, if you remember before, we printed a value, we called the function, we came back, and the old value was still there. Well, now it's totally different because we're passing an alias to the value. Okay, so let's go through these examples. Here in main, I've got num initialized to 10 and another num initialized to 20. So now what I'm doing is I'm calling pass by ref1, and I'm passing num into it. So before I call it, I expect this to display a 10. But then after I call it, I don't expect the 10 anymore because I've passed a reference. Instead, if you look at pass by ref1, num is 1,000. So I expect num to change. All right, so let me run this and then we'll walk through exactly what's going on. There you go. Before calling pass by ref1, we have a 10. After calling pass by ref1, we have 1,000. If you remember the way it was with call by value, we had 10 and 10. All right, so let's see what's really going on here. Let me scroll up just a little bit. There we go. Okay, so I'm in main, and I've got num is 10. And I'm displaying it right here, right? So that's going to display a 10 in that output statement right here. But then I'm calling pass by ref. So I'm going to call pass by ref 1 over here. And it has a variable. And if you remember what that variable was, let me scroll up. It's right here. It's also called num. Remember, this could be any other name. They just happen to be the same name in this case. So that's got a variable in there called num. And right here, what's happening is when I pass this num into it, then this num now becomes an alias to that num. Okay, and again, don't worry about the names. I'm going to use a different name next time, but it's common to many times use the same name, so don't let that confuse you. And then in here, I'm saying num equals, I believe it was 1,000. So what's happening is this is an alias to this number, so this guy's going to change to 1,000. Real different to call by value. Okay, so in this case, we are really passing in the location of the number behind the scenes. But we don't have to worry about it because syntactically it's the same as call by value. Let's take a look at another example here. I'll scroll down just a little bit, and here we've got the same call to pass by ref1, except we're passing in another number. right? In this case, another num is 20. So this will display a 20, and when I get back, it will have changed also. There it is, 10, 1,000. Now we've got another num was 20, and now it's 1,000. So you can see that we're passing that by reference, and the alias is actually referring to the actual parameter. That's the important part to really understand here. In this example, let's take a look at that. If you recall this one, let me scroll up just a little bit so you can see it. Right here, pass by ref2 expects a reference to a string, and it just assigns changed to that string. Okay, so let's walk through this one and see what we can expect. In this case, I've got this variable right here, name, which is Frank, and it's in main. And it's a string object, right? Then I call pass by ref2. So here's pass by ref2. And it has a variable over there called s. That's the formal parameter. And what we're doing here is we're passing by reference. So we're passing name over here, and this s will now be an alias to name. So it's really referring to the actual parameter. Remember, this right here is the actual parameter. So now when I change this to changed, nothing happens over here. It's actually happening over here. So this is gone. It's now changed. So when this function is done, my actual parameter has changed, in this case to changed. Okay, so let's run this example, and we'll be able to see that that string really does change. You see that right there? Name before calling pass by ref2 is Frank. Name after calling pass by ref2 is changed. Pretty easy. It's really up to you, and when you're designing, do you need the actual changed or not? If you do need it changed, you pass it by reference. If you don't need it changed, you do pass by value. Sometimes pass by value is very expensive, as I mentioned before, so you want to pass by reference and then qualify it to be constant. And that's what we'll do in the print function a little bit. But let's take a look at this one here. Okay, so this is the last example we'll look at right here. Remember, we're calling pass by ref3. What it does is clears out that vector. So it's going to remove all the vector elements. It's going to make the vector empty. Okay, so let's do that. All right, so we're here. This is Stooges. And again, Stooges is declared in main. So Stooges is basically 3 strings, Larry, Moe, and Curly. And they're in a vector. Okay, so now I'm going to print the vector, and I'm going to pass Stooges into print vector. Now the vector is also expecting a reference, in this case a constant reference, so I can't change anything. So what happens is when I call print, vector, variable over there called v, and since I'm doing pass by reference, this refers to this. So whenever I do any operation on v, it's affecting the Stooges vector, right? That would be the case, but since this is const, is read only. There's no changes allowed, but I avoid the whole copy issue, which is important. All right, so that takes care of print. Now, when I call pass by reference 3, I do exactly the same thing, right? So I call pass by reference 3. I've got my vector, and it's also pointing to Stooges. Now, when I say v.clear, I'm clearing this out now, right? So Stooges is empty now. When this function is done, it's gone, and my vector is empty. So when I print it out again right here, you'll see nothing print. If you recall in the pass by value, it printed out Larry, Moe, and Curly again, right? Here, nothing. So let's run this. And you could see right here, Stooges before calling pass by ref3, Larry, Moe, Curly. After calling it, empty. Why is it empty? Because pass by ref3 cleared out that vector. It deleted all the elements. And because I'm passing by reference, it's really affecting the actual object. If I didn't want this to happen, I would make this const, in which case this won't compile anymore because you're not allowing me to change the vector, which is what this is doing. You'll get a lot of chances to play with this in the challenge at the end of this section, but that's pass by reference. We can use it with simple primitive types, or we can use it with object types. It basically works the same way. Just think of it as an alias to the actual parameter. In this video, we'll learn a little bit more about C++'s scope rules. C++ uses scope rules to determine when and where an identifier can be used. It uses static or lexical scoping, which means that the scope is determined the same way you read a program. C++ has two main scopes, local scope and global scope. Local or block scope refers to the visibility of an identifier that's been declared in a block, that is, a set of open or closed curly braces. Function parameters also have block scope. These identifiers are visible within the block in which they're declared. I talked about this earlier in the course, but it's important to understand it in the context of functions. When a function is called, you can think of the function as being activated, and the function parameters are bound to storage. They become alive, and their lifetime is while the function is executing. Once the function completes, the function is deactivated and these variables and parameters are no longer alive. That doesn't mean that they're somehow marked as unavailable. It simply means that the compiler doesn't recognize them any longer, and the storage they were bound to will likely be reused. That means that the values of local variables are not preserved between function calls. If we have nested blocks, then statements in the inner blocks can see identifiers declared in the outer blocks, but outer blocks cannot see variables defined in the inner blocks. However, there is one type of variable whose value is preserved between function calls. This is a static local variable. It's a variable whose lifetime is the lifetime of the program, but it's only visible to the statements in the function body. These variables can come in very handy when you need to know a previous value in a function without having to pass it in all the time. Static local variables are only initialized once. If no initializer is provided, they're set to 0. Identifiers with global scope are identifiers that are declared outside of any function or class. These identifiers are visible to all parts of the program following their declaration. Best practice with identifiers with global scope is that it's okay to use global constants, but global variables should be avoided. Let's see scope rules in action in the IDE. Okay, so now I'm in the CodeLight IDE, and I'm in the Section 11 workspace in the Scope Example project. And here I've got an example program that just exercises a few of the scope rules, and I'll walk through them. They're very straightforward. The nice thing about languages like C++ and other languages that use static scoping is that the scoping is lexical, so it's as you read code. It's not something that's happening at runtime on the call stack. Languages that use dynamic scoping rules are a little harder to follow in this sense. So let's take a look at this example here. I've got my main, and I've got two local variables defined in main. They're local to main because they're defined inside those brackets. Okay, that's really important. So what's this scoping deal all about? Well, when I use a variable name, for example, I'm using num here. Which num am I talking about? That's what scope is all about. And the rule is really very simple. First, you look inside your own scope, inside your local scope. So here's num, I'm using it. Which one is it? Well, look inside your scope here. You'll see it's this one right here. Right? That's the closest one within that you're in. So this is going to print 100. Now, block statements, just like we had here, block statements create a new level of scope. And we're going to see this again when we use classes. So every time that you create a block, you've got a new level of scope. So notice here I'm declaring num again. This is a different num now. I'm using the same name on purpose. So now when I use it here in the output statement, which num am I talking about? Am I talking about this one here on line 36, or am I talking about the one on line 42? Well, you look in your closest scope first, right? You look for a local variable. So this num here refers to this num right here. That's the variable. So this is going to display 200. What about this one here? Num1. The rule again that you follow, look inside here first. Do you see a num1 declared in here? No, you don't. Then you look out to your outer scope. There it is right here. So that's the one I'm using. And that'll display 500. Okay, hopefully that makes sense. Now, here we go. We're using num again. But now we've got two nums. We've got the num here on line 36, and we've got the num here on line 42. Which one do we use? Well, you look in your level of scope, your local variable. You can't look into another block. You notice how this block here could see out, so we could see num1. That's perfectly normal. First you look in your local scope, then you look outwards. You don't look inwards. Okay, so this num refers to this guy right here on line 36. So this is going to display 100 as well. We'll go through a few more examples down here, but let's run this one first. We're expecting 100, 200, 500, and 100. So let me run this example. And here we go, 100, 200, 500, and 100. Just what we expected. When you read about scope in books and on websites and tutorials, it's really complicated when you first learn about it. You're talking local, non-local, global, and all this stuff. But conceptually, it's pretty straightforward. First, you look local, then you look out, 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 as far as you need to go until you find it. If you don't find it, you have a compiler error for sure. All right, so let's look at this one here. I'm calling a function called local example, and I'm passing in a 10. And let me show you what that function looks like. It's right here. Let me expand it a little. So I'm calling this with a 10. So I'm passing in a 10 by value. So this x right here will be a 10, right? I'm going to copy the 10. I've got a num variable right here, and I'm initializing it to 1,000. So my output statement is using num. Which num am I using? Well, I've got two choices, right? I can use this one on line 20, or I can use this one on line 11. I always use the local variable. In this case, I'm going to use this one on line 20. So this is going to display 1,000. Then I'm setting num equal to x. Okay, x is 10. Which num am I talking about? I'm talking about this num again. Right? So I'm going to set this to 10. And I'm going to display num, which is again the 10. So this will display 1,010. Notice that I can't use num1 here. Okay, because it's not within the scope that was defined inside main. So I run this, I expect 1,010, and let's try that out. And here you go, local num is 1,000, and then local num is 10. Suppose I call this again, but I pass in a 20. What happened? Well, let's go back here again. In this case, I'm passing in a 20, so x is going to get the 20. I'm initializing this to 1,000. Every time I call this function, that num will be initialized to 1,000. So in this case, there's num. I'm using this one right here again. So this will display 1,000. Now I'm setting that same variable to 20, and then I'm displaying it right here. So this is going to display 1,020. Okay, so it's the same idea, and it's pretty straightforward. Let me run this. So we thought we saw 1,010. Now we're going to see 1,020. Okay, so now let's look at an example of a global variable. You'll notice that way up here at the top of the program, I'm going to scroll all the way up. Let me close that function and expand this one. This is what we've got right here. We've got a global variable called num right here on line 11. And I'm initializing that global variable to 300. How do I know it's a global variable? It's not declared inside any function. It's not declared inside any class. It's just sitting there all on its own, right? This is global to the entire program. So in this case, I'm calling global example. And which num do I use? Well, what's the first thing you do? You look in here. Is there a variable called num defined in here? No, there isn't. Then you look outward, and there it is. So this displays 300. Then I take num and I multiply it by 2. Okay, which num? Same one. So this will now become 600. And I'm going to display 600. Okay. Now, what if I call this function again? And I'll call it twice in the main. What if I call it again? Well, the next time I call it, this variable still has 600 in it. It's a global variable. So the next time I call it, we look at num. Num is 600, which I display. I multiply it by 2. Okay, so that's 1,200 now. And then I display it again. So it's 1,200 this time. Notice the global variable does not get reinitialized every time. It only gets initialized that one time when you're actually before main is even called, that's initialized. So here we're going to end up with 300, 600, and then 600 and 1,200. So let me uncomment that one line out so we can call this twice right here. And let's run that. And you can see here we've got 300, 600, 1,200. Just what we would expect. All right, so let's look at one more example here, is the static local example. And I'll scroll up. Let me close that down. Now, we mentioned what a static variable was. A static variable is a variable that is defined locally. In this case, this is a static local variable in here. But because we're using the static qualifier, what that means is that this num variable will be initialized to 5,000 the first time this function is called. After that, it retains its previous value. Real different from the example value, which it got reinitialized every time. Right? So let's say I call static local example the first time. We're initializing num to 5,000. That only happens once. Then I'm using it. Which one? Again, I'm looking inside local scope first. So that's going to display 5,000 here. Then I'm incrementing num by 1,000. Okay. Now it's 6,000. And then I'm displaying it again. Well, now it's 6,000. Now, suppose I call static local again. Since this has already been initialized, it won't be initialized again. And it's going to retain its previous value. So it's 6,000 right now. Here it is. So if I display it, I'm going to get a 6,000. And then I'm going to increment it again by 1,000 and display it again. So I'm going to get 7,000. And when I run this a third time, I'll end up with the 7,000 I started with and the 8,000 that I end up with. So as you can see, it's pretty straightforward. This is a real useful concept, the concept of static local variables, because you've got a number, or a variable in this case, that behaves like a global variable, right? Because it's retaining its value, but its scope is local. So you don't have the same problems that you have with global variables, which means that they're visible throughout the program and any piece of code could change it. In this case, if this number variable right here gets a really strange value, the only place it could have gotten it from was inside this function, and you know exactly where to look. So that wraps up scope. It's a pretty simple concept, and it's, again, think, look local first, then look out, then look out, then look out until you hit global scope. If you don't find that variable there, then you've got a compiler error. So how do function calls work? Functions use an area in memory called the function call stack or program stack. A stack is analogous to a stack of books or a stack of dishes. If you place a book on top of the stack, then you must remove that book before removing any others. This is referred to as last in, first out, or LIFO. Stacks also use the terms push when you put an item on top of the stack and pop when you remove an item from the top of the stack. In the case of a C++ program, these items are called stack frames or activation records. All it is a collection of information that represents an active function. So this is where parameters are stored, local variables, the return address, and more. Each time a function is called, an activation record is created, and it's pushed onto the call stack. When the function terminates, we pop its activation record off the call stack, and now the top of the stack is the function that just called the one we just popped off. The call stack works in a very orderly manner. You can't jump into or out of the middle of the stack. You must follow the LIFO rules. Also remember that the call stack is finite in size. If you activate too many functions on the call stack, then it's possible to run out of stack space. This results in a stack overflow error, which is usually an unrecoverable error, and your program will terminate. The best way to understand how function calls work is to show you visually. Let's do that now. In order to understand how function calls work, we really need to understand how memory is laid out. Here, let's say that this is the memory for our program. It's divided into segments. So here we've got the code area. This is where the code resides. We've got an area for static variables or for global variables. That's where they're stored right here. And here's the area for the stack. This is the function call stack. And this is what we're really concerned about in this video. So this is the area I'm going to concentrate on in this video. Then we've got another area in memory here called the heap or the free store. We'll talk a lot about this area when we talk about pointers and dynamic memory allocation. So in this video, keep in mind that what I'm talking about is this area right here. That's the function call stack. So when we call functions and they finish and they pop off the stack, this is what we're talking about, this area in memory right here. Okay, so I'm in the IDE and I'm in the Section 11 workspace in the How Function Calls Work project. And I've got a real simple example here that I'm going to walk through in detail in a second. But before I do that, let's concentrate and look at what typically happens when one function calls another. So I've written it out here, and this is not the only way to achieve this. There's a lot of different ways to get to the same end. But this is what typically happens. So suppose I have a main, and that main calls a function called func1. That's what's happening here. I've got main, and it's calling func1. Okay. And what happens? Well, main pushes space on the stack. Remember, everything here is based on the stack for the return value. That function, func1, is going to return something to main. Main is the one that needs to get that result once that function is done. We need to push space for the parameters that are being passed in, if any. In this case, we've got two right here, x and y. And we need to push the return address. That's important because function 1 needs to know where to come back to. Then we transfer control over to function 1, which is basically an assembly language instruction called jump. You just jump over there and you're off and running, so control is transferred. Now on function 1 side, it pushes the address of the previous activation record. That's basically moving a stack pointer. That way you know where the top of the stack is. You push any register values that need to be restored. Then you perform the code in function 1. When the code is finished, you restore the register values. That way main is where it was before. You restore the previous activation record, right? You basically pop all this stuff off the stack. You store any function result where main wants it. You can see main gave you the address. And you transfer control back to main. So you jump back to that return address that main pushed. On main side now, remember, function 1 is now done. So main knows where the parameters are and it knows where the return values are. So it needs to pop that information off the stack to clear up the stack and also grab those values if it can. Okay, so this is the general flow. We're not going to cover all the details here. I'm more interested in the parameter side of it. So what I'm going to do is I'm going to walk through this example and I'll draw a function call stack over here and we'll go through it in detail so you can see exactly what's going on from the parameter perspective. I'm not going to worry about stack pointers and static links and dynamic links and all the stuff that's on an activation record, but more generally, let's worry about the parameter passing so you can really understand what's going on, because it's important to understand this, especially when we learn about recursion later on. Okay, so let's walk through this example. Program execution starts at the main. So main is going to be activated. It's got a function activation record because it is a function. So let's assume here main is on the stack already. And main has an X, it's got a Y, and it's got a Z. So we need space for those local variables. You can see X is initialized to 10, Y is initialized to 20, and Z is 0 in this case. Okay, so now main is right here, and we're executing this piece of code. Z equals function 1 with XY. So we're calling function 1. So what happens is main stops what it's doing. It allocates space for XY, and I'm just going to do this conceptually so we don't waste a lot of time, diddling with the stack and pointers and things. But let's suppose that at this point we're going to push an activation record on here for function 1. And this is a little different from the example I showed you that I just walked through, but it's a little easier to draw. So this is where we're at. So now we're at function 1. Function 1 is now on the stack, and we need space for A, B, and result. Okay, so let's say we've got A, we've got B, and we've got result. We're doing pass by value here. So what's going to happen is the X hooks up with the A, and the Y hooks up with the B, right? There's your actual formal correspondence here. So X is 10, and that goes copied into the A. Y is 20 in this case, so we're going to copy that to the B. Okay, so this is where we're at right now. Now, let me clear a little bit of this up. All right, so that's where we're at now. Now we start executing this function, function 1. So it's going to add A and B. Okay, so that would be 20 plus 10. So this gives me a 30. And it's going to store that value into result right here. So now result gets a 30. Originally result was 0, right? Because I zeroed it out here. I didn't write it on here, but you get the idea here. Now we're going to call function 2. And we're going to pass in result, A and B. Okay, so again, let's stop what we're doing here. We need to come back and finish this code. So we're here, and now we're activating function 2. And all along, those stack pointers are moving along here. This is the part that I'm not going to worry about drawing here. Okay. So now we're in function 2. We need space for X, Y, and Z. But notice X is a reference parameter. Okay, so we'll have to deal with that. So we've got X, Y, and Z. All right, so let's do X, Y, and Z. All right, let's do Y and Z first. We're going to pass those by value. What is Y and Z? Well, we've got three here. We've got result, which is corresponding to X. A corresponds to Y, and B corresponds to Z, right? So Y gets the value of A. The value of A was 10, so Y is going to get 10. And Z gets the value of B. So B was 20, Z is going to be 20. Okay, now let's talk about that reference parameter. Remember when we talked about reference parameters, we said that there were aliases, right? So in this case, X is an alias for result right here. Okay. So X is an alias for result. So any changes I make to X, result will be updated, right? Because that's the whole idea. That's the whole point of pass by reference. Now we start executing this code. The code says X equals X plus Y plus Z. That's what that means right there. Okay, so we've got Y and Z here, which are 10 and 20. So this becomes 10 plus 20. And then what's X? Well, X is a reference to result. Result is 30. So we're going to grab the 30 and add those two together. That gives us 60. So now we're going to say X equals 60. Well, again, X is an alias for result. So what we're doing is we're updating that guy to 60 right here. Okay, now function 2 is done. So what happens? It gets popped off the stack. So let's do that. So function 2 is now gone from here. All that's gone. I'm back in function 1. Well, where did function 1 leave off? It left off right here. We're back from the function call now. So it needs to return result. What's result? 60. Where's it going to return result to? Right here. Remember, result right there is the result of that function call. So what I'm going to do here is I'm basically going to say Z equals 60. Okay, so that's what's happening here. I'm popping off the stack now. So function 1 is done. All this is gone. I'm back to main, and all main has to do is that one output statement right here, which displays Z, and Z is now 60, and the program's done. Okay. So this gives you an idea of conceptually what's going on with function calling. Now, I skipped a lot of these steps here on purpose because there's a lot to draw and it gets really, really cluttered. But think about all this as function call overhead. You really don't have to worry about pushing registers and transferring control, and all that's done for you by the compiler. But there is a certain amount of function call overhead here. So let's run this program and see that we indeed get a 60. And there it is. There's the result. There's 60. Okay, so hopefully this works. We'll do this again when we talk about recursion. That's when a function calls a function calls a function calls itself. So it's really important to understand what's going on with the stack call frame, so we really know what's being passed and what's being returned. And you can see here that if we don't have a way to unwind to get back to where we were, we could just really run out of memory, right, and get a stack over. As we saw in the previous video, function calls have a certain amount of overhead. We need to create an activation record, push it on the stack, deal with parameters, pop off the activation record when the function terminates, and deal with the return addresses and return values. Although all of this can happen very quickly and efficiently, it still happens. Sometimes we have a very simple function, and the function call overhead might be greater than the time spent executing the function. In cases such as these, we can suggest to the compiler that it generate inline code. Inline code is basically inline assembly code that avoids the function call overhead. Inline code is generally faster, but if you inline a function many times, then you're duplicating function code in many places, and it could lead to larger binaries. That said, compilers are so sophisticated now that they'll likely inline code even without your suggestion. Let's see what an inline function looks like. Here you can see the syntax for an inline function. We simply precede the function return type with the keyword inline. Inline functions are usually declared in header or .h files, since the definition must be available to every source file that uses it. As mentioned earlier, compilers are so good now that most will make short functions like this inline anyway, even if you don't provide the inline keyword. Don't worry too much about asking the compiler to inline your functions, but now you know what inline functions are in case you see them in C++ code out there. In this video, we'll learn about recursive functions and how to implement them in C++. A recursive function is a function that calls itself. The function can call itself directly or indirectly through another function. If we end up with two or more activation records on the stack for the same function, then we have recursion. Recursion is great for certain classes of problems. Recursive problem solving is something that most programmers have a little trouble doing when they first learn. That's normal. Eventually, you'll understand that recursive solutions make sense in certain cases. There are many types of recursive problems that lend themselves well to a recursive solution. In mathematics, we have factorial, Fibonacci numbers, fractals, and many more. In searching and sorting, we have binary searches, search trees, depth-first search, graphs, and also many more. There are also classic problems like the Towers of Hanoi that can really be hard to solve with a non-recursive solution. Let's see how we can calculate the factorial of a number using recursion. Here we see the definition for factorial as you would find in a math book. Factorial is defined in terms of itself. That's what recursion is all about. We have a base case. So in this case, factorial of 0 is 1 by definition. And we have the recursive case. Factorial of n, or n factorial, is equal to n times n minus 1 factorial. See the recursion there. Let's see how we can implement this in C++. So let's look at the code starting at main. We call factorial and pass in an 8 to the factorial function. When the factorial function returns, the value returned will be output to the console. In this case, we expect 40,320. Okay, so now let's look at the factorial function itself. First, we need to decide what types we'll accept and return. The factorial function can generate massively huge numbers. So in this case, I'm using unsigned long as the return type and the parameter type. This can hold very, very large positive integers, but we can still get an overflow even with such a big number. If you look at the code for the factorial function, it looks exactly like the mathematical definition of factorial. We check a base case. In this case, if n is equal to 0, we return 1. Remember, the return knocks you out of the function immediately. Otherwise, we return the result of calling the factorial function again with n minus 1. So in this case, it would be return n times call factorial with n minus 1. There's the recursion. The base case is super important since it's what stops the recursion. Otherwise, we would recurse indefinitely and eventually we would run out of stack space and get a stack overflow error. In a bit, we'll head over to the IDE and I'll walk you step by step in detail through an example call to factorial so you can see exactly what's happening on the stack. Let's look at calculating a Fibonacci number now. Here's the definition for a Fibonacci number. There are two base cases. Fibonacci of 0 is 0 and Fibonacci of 1 is 1. And the recursive case is Fibonacci of n is equal to Fibonacci of n minus 1 plus the Fibonacci of n minus 2. Again, notice the recursive definition. Fibonacci is defined in terms of itself. I think you can see how to implement this in C++. Again, I've decided to use unsigned long since Fibonacci can also produce huge numbers. Notice in the main, I call Fibonacci and the result I expect back is 832,040. Now let's look at the Fibonacci function. Notice the handling of the base cases. If n is less than or equal to 1, then we simply return n. So when n is 0, we return 0, and when n is 1, we return 1. That handles both base cases in one step. We could easily rewrite this condition to explicitly check n equals 0 and n equals 1, but this achieves the same result. This base case is what stops the recursion. If n is not 0 or 1, then we call Fibonacci again with both pieces of the problem definition. Eventually, the recursion will stop and the result will be returned to main. Notice how much the code looks like the mathematical definition of Fibonacci. This is by design. Let me give you a few thoughts on recursion. Remember, recursion is a form of iteration, so anything that can be done recursively can also be done with iteration and vice versa. Use recursion only when it makes sense. The problem must lend itself to a recursive solution. Don't use recursion to count from 1 to 10. Remember the base cases. They are what stops the recursion and are super important. Because of the call stack, recursion can be quite resource intensive, especially if you have very deep recursion. It's not uncommon when you're first learning recursion to recurse indefinitely and run out of stack space, resulting in a Stack Overflow error. That's perfectly fine. This is how you learn. I can't tell you how many times in my career I've seen recursive functions rewritten to iterative solutions because of resource issues. Generally, an iterative solution to a recursively defined problem is less elegant and more difficult to understand in code. But sometimes we have to meet non-functional requirements, and that's what it takes. Let's head over to the IDE and walk through a factorial example in detail. So I'm in the IDE. I'm in the Section 11 workspace. And there are two projects that are interesting here that both use recursive functions. One is the Fibonacci project, and the other is the factorial project. We'll walk through a detailed example of how factorial works recursively in a minute. But here's Fibonacci, and it's just like I wrote in the slides. So here in the main, I'm calculating the Fibonacci number for 5, 30, and 40. You can see the 40 is pretty large. If you try to do like a Fibonacci of 50 or something like that, it's going to take a while because there's a lot of recursion going on. I mean, it all depends on how fast your machine is. Even here, when I do a Fibonacci of 40, I'll run this, and you'll see a little bit of a delay. You see that? It took just over a second delay there to actually calculate that Fibonacci number, and it's a pretty large number. But once you start getting to really large numbers here, for example, 45, 50, then the recursion is just tremendous, and it takes a while to solve those problems. Okay, so let me go back to factorial. That's the one I really want to go over here. So here's the factorial, just like we wrote it, the factorial of some number. And there's 4 examples here. You can see factorial 3 is 6, factorial of 8 is 4320, and so forth. You can see the factorial of 20 is a really big number. And as this number grows here, that number really grows big time. So let me run this, and it's fast here. But once you start really increasing that number there, it's going to slow down big time. Now, what I want to do is I'm going to comment these out just for a minute, because I'm only interested in factorial of 3. I want to walk through a stack example of exactly what's going on when we call factorial with a 3. We could do a 4 or 5 or a 6. If we did that, we'd be here all day drawing stuff on the stack because of the recursion. 3 is an easy number. It'll be pretty easy to do on a stack, and it won't take so long. But you'll understand exactly what's happening, and whether you use 3 or 4 or 5, you'll understand. Okay, so let's do that now. Okay, so here's my stack, and my main is on the stack, and all main is doing is it's outputting the result of factorial with a 3. So I'm just going to use fact rather than write out the entire word factorial. So main is calling factorial with a 3, and the result it gets back is going to output, right? Okay, so that's simple enough. So what happens? Well, main calls that function factorial, right? So we're going to activate that function, and we'll put it on the stack. So main is going to call factorial with a 3. So here's the activation record for factorial from this call right here from main. Notice the factorial function right here has one local variable, n. So we need to allocate storage for it. And let's say that that's n right here. And what's the value for n? Well, in this case, it's 3, right? I'm passing 3 into this function. So n is going to get a 3. Okay, now I'm going to write the code right here in the stack. The code doesn't exist on the stack. It exists somewhere else. But here you'll be able to follow it easier, I think. So what do? We start executing the code. Is n equal to 0? No, n is equal to 3. So what do? I return, I'm just going to write n, which is 3, times factorial of n minus 1. Well, 3 minus 1 is 2. So we need to call that function. So what do? Again, we transfer control to the other function. Function is it? It's the same one. We're just calling it recursively. So in this case, what am I doing? I'm calling factorial with a 2. Factorial has an n, so we need to allocate storage for an n. It's just another activation record. In this case, n is 2. Let's start executing. Is n equal to 0? No. So I want to return n, which is 2, times factorial of n minus 1. Well, 2 minus 1 is 1. So I'm going to do that. Okay. Now, notice what just happened. I've got 2 activation records on the stack for the same function. That's the definition of recursion. All right, so now what are we going to do? We're going to call factorial with a 1. And you can see the stack just growing, right? Well, factorial is the same function. It's got an n. In this case, I'm calling it with a 1. I'm passing the n by value, so there's the 1. And what does it do? Is n equal to 0? Nope. So it's going to return n, which is 1 times factorial of n minus 1, which in this case is 0. So what do? Again, I stop and I call factorial again, in this case with a 0. So let's do that. Well, here we're going to call factorial with a 0. N gets a 0. Now we're here. This is the base case. Finally, we're going to start unwinding. Is n equal to 0? Yes. So what do? I return 1. Return 1 to who? To whoever called me. Well, here's the call right here. So the value of that call will be 1. Okay? And now what we do is we start unwinding. So this gets popped off the stack. And now we're here. Well, this guy can now return as well, right? So it's going to return 1. It's going to return 1 times 1. 1 times 1 to who? To this guy right here. So 1 times 1 is 1. And we're going to pop off the stack. So this function now is gone. That activation record gets cleaned up. And we're here, right? So hopefully everybody's with me. It's pretty straightforward. It's just a matter of keeping all your ducks in a row. So here we're going to return 2 times 1, which is 2. To who? To this function call. That's the value of that function call. That's the 2. And again, we're going to clean up the stack. It gets popped off. That activation record, all those areas in the stack that we allocated are gone. So now we're here. Finally, we can calculate this result, which is 3 times 2, which is 6. So we're going to return 6 to who? This guy is the one that called me. That's a 6 right there, right? The value of that function call is a 6. What are we going to do now? Pop off the stack. We're cleaning up finally. You see, that's called unwinding from a recursive call. So we're here. Now we've got a 6. And what do we do with the 6? We output it. And that's the final result of the call to factorial with a 3. Okay, so you can see it's pretty straightforward. It's a matter of your recursive calls get pushed on the stack, and then you start unwinding. The unwinding is starting right there. That's the critical piece, that base case. If you forget that base case or get it wrong, then this will just keep going, and eventually you're going to run out of stack space and get a stack overflow error. Okay, so there you go. Obviously, if you remember the Fibonacci function, it's more complicated than this, right? Because let me go back to it so you can see. The Fibonacci function, which was right here, has 2 pieces of recursion, right? So we're going to have to call recursive functions, calling itself, obviously, but it's calling it twice per call. So the amount of stack space that's used is larger. That's why Fibonacci takes longer than factorial to execute, especially with very large numbers. Okay, so hopefully this diagram helps. Recursion makes a lot of sense. Once you understand what's really going on the stack, I think it totally makes sense. All right, congratulations for making it through this section. We covered a lot of material in this section. Hopefully you have a pretty good grasp of C++ functions and how they work. Now you're ready for a challenge. This challenge won't be easy. Remember the challenge from section 9? In that challenge, we had a vector of integers, and we wrote a menu-driven system that allowed the user to display the numbers, add a number to the list, calculate the mean, the smallest, and the largest. That challenge was all about applying what you learned up to that point in the course and let you use control flow statements like loops and if statements. Well, for this challenge, we're going to solve that problem all over again, except this time our solution will be modularized in terms of functions. You can start with your solution and refactor it so that it uses functions, or you can start with my solution, which is included in the challenge project in Workspace 11. Or you could start this challenge from scratch. It's really up to you. Let me give you a few hints and tips for this challenge. Remember, this is not an easy challenge, so if you get frustrated, take a break, come back to it later. Here are a few hints. Create functions for each of the major functions in the program. Keep the functions small. Remember the boss worker analogy. Keep the vector declaration in the main function and pass the vector object to any function that requires it. Don't be tempted to move that vector object outside the main and make it a global variable. That will really defeat the whole purpose of this exercise. Now you can start defining a function that displays them. It's a real simple function. Call it display menu. And all it is a bunch of output statements. And then you can call that function whenever you need to display the menu. You can then define a function that reads the selection from the user and returns it in uppercase. That way we don't have to deal with checking lowercase and uppercase selections. Then create functions for each menu option. And then finally, create functions that display the list of numbers, function that calculates the mean, a function that looks for the smallest and the largest, and so forth. Take it one function at a time and take your time. Again, if you get frustrated, take a break. Finally, don't forget to use function prototypes. Use them. Let the compiler help you every step of the way. All right, good luck. I know you can do it. When you're finished, compare it to my solution, which is in the next video. Hello everyone, welcome back. This is the solution to the Section 11 challenge, and I'm in the Section 11 workspace in the Challenge Solution project. I'd like to go over one possible solution to this project. This is a solution that I've done, very modular. All the functions are there. They're all small. They do one thing and they do them well. So let's go through this. Let's look at our main first. Let's start there. Main defines numbers, which is the vector of integers, just like we've had before. And it's got a character variable called selection. That's where the user is going to type in their selection, their menu selection. And now we've got our do loop. Our do loop, now I've folded the code here. There's obviously more code here in the switch statement, but I'm just going to show you the overall structure of this loop. So here we're doing do display the menu. Notice that now we're calling a function to display the menu. Then I'm going to get the selection from the user. So whatever they type in, I'm going to store in selection. But I'm not just going to store it in selection. I want to make it uppercase and then store it in selection. That way I don't have to check lowercase and uppercase every time I check for a selection. And I want to do this loop while the selection is not equal to an uppercase Q. Okay, so that's pretty much it. Now let's take a look at our display menu function. And it's right down here. And I'll expand it right now. And you can see that that's the function display menu. And all it is the output statements, just like we had before inside the main. So in this case, whenever I need to display the menu, I can call this function, and I'm doing that exactly here. Okay, now let's take a look at the getSelection function. Here's the getSelection function, and you can see the name of the function is getSelection. It expects nothing, but it does return a character. So in this case, I'm defining another character variable in here. Remember, this variable here is local to this function. I'm simply reading from the keyboard their selection, and I'm converting it to uppercase and returning it. Okay, so that's that one. So at this point, I've displayed the menu, and remember, the menu has at the very bottom of the menu, enter your choice. So I don't really need to prompt the user for anything. It's already there. So I'm displaying the menu, I'm getting their selection, and selection will now contain an uppercase character. Okay, perfect. So now, we're going to switch off of that character. And let me expand the switch statement here. So in this case, if the selection is a P, I'm going to call a function called handleDisplay, because remember, P is to print out all the integers in the vector. And I'm going to pass in the vector to that function. If it's an A, I'm going to do a handleAdd. M is handleMean, S is handleSmallest, L is handleLargest, Q is handleQuit, and default, I'm just going to handle an unknown. So you can see now that the logic in main is exactly like it was before, except we're calling functions. We don't have all that code written in here. Also, this allows us to think modularly, right? Now I've got functions doing those defined tasks. So again, it's that boss worker analogy at work here. It's perfect for that. Let's take a look at handleDisplay. So in this case, so the user selects P. Notice I don't have to check uppercase and lowercase anymore because the getSelection function already made everything uppercase. So I'm going to call handleDisplay, and I'm going to pass in the vector to it because obviously it needs to display the vector. Let's come over here to handleDisplay, and you can see the function right here. Now notice handleDisplay, it expects a vector, and I'm passing that vector in by reference and const. Just as we've spoken about before, this display method really has no business changing that vector, so I'm not going to even take the chance that it will. I'm passing in it by reference, so I don't have to copy it, and const. So let's take a look at that. All right, so we've got our vector here. So I'm checking to see if the size of the vector is 0, in which case it's empty, and I'm displaying the list is empty. Otherwise, I'm calling a function called display the list, and I'm passing in that vector. The same vector I got, I'm passing to the function. I could have looped in here and displayed the list right in here, of course, but I decided to create another function because, we could tweak the behavior of what the display looks like, and I don't want all that code in here unnecessarily. So let's take a look at display list. It's toward the bottom. I'm going to scroll down here. There's the display list function right here. Again, it expects the same vector that was sent to the function prior. And now if you look at the code, it's going to print out a left bracket. Then it's going to loop through that vector and print out each number, just like before. But you can see that this list displays just the list. That's all it does. And whenever I need to display a list of integers, I can just send it right into this function. Okay, so that's display list. I'll scroll back up. And let's talk about handle add. So now we're here, handle add. It's another function. Whenever the user presses A, they want to add a number to the list, right? So I want to call handle add and I want to pass the list, the vector. So let's see the handle add method. I'll scroll down slightly and we'll see handle add is right here. Now notice that in this case, I'm still passing the vector by reference because I want to add an integer to it, right? So I need to have the reference to it, but not const because I need to change it. I need to ask the user for an integer and store it in the vector. So let's look for that code. We're doing everything right in here. We're saying there's an integer called num to add. Remember your scope rules here. That integer is local to this function. I'm asking the user to enter an integer to add to the list. I'm getting that integer from them from the keyboard. And then I'm simply calling the pushback method of the vector class with the number to add and displaying the message. That's it. Really, really easy. Okay, so let me go back up to the main and let's see handle mean. How does that work? Well, we'll go to the handle mean function, which is right here. Again, it expects a reference to a vector and it's constant. I don't want my handle mean modifying the vector. So what do? We check to see if the vector is empty. If it is, we just say unable to calculate the mean, the list is empty. Otherwise, we call calculate mean and we pass in the vector. It's going to return a double to me, which I'm going to display right in here. So it's going to say the mean is whatever number I get back. All right, so let's take a look at calculate mean. I'll scroll down here. There's calculate mean. Notice again, it's the same vector, same syntax here. By reference, constant. There's my total. I'm looping through those numbers, adding them all up to total, and then I'm casting one of these to a double and dividing by the size, exactly like we had before. It's pretty much the same code that we had in the prior challenge, the section 9 challenge, except we're breaking it up into modules here. So that's it. That's calculate mean. And I think you can see where we're going with the rest of this. Here is, let me close up handle mean. We've got handle smallest, handle largest, work exactly the same way. And then handle quit and handle unknown. We're really doing very little in there, but I decided to make them functions because you never know what you need to do in there. I mean, suppose you're working with files and the user quits and you want to, close up files and so forth. I'd like to do that in a function and not here in the main. I want to keep my main really, really simple, easy to read and straightforward. So my handle quit kind of looks like this. Right here, you can see handle quit. All it's saying is goodbye. And my handle unknown is saying unknown selection. I guess I should spell that right. Unknown selection, try again. Okay, so that's pretty much the solution. Let me scroll up to the top and I've got all the function prototypes at the top. So there are my function prototypes. Here are the prototypes for displaying the menu and getting the user selection. Display the menu, expects nothing, returns nothing. Get selection, expects nothing, returns a character. Then I've got my menu handling function prototypes. Notice that all of them expect a reference to the vector that's constant, except handle add, because handle add needs to change the vector, so it can't be constant. Then I've got handle quit, handle unknown, and then I've got the functions that actually do the work, right? The display list displays the list, calculate mean, give me the vector, I'll give you back the double, that's the mean. Get smallest, same idea. Get largest, same idea, except we're returning an integer. Okay, so what do we want to do? Let's modify this program a little bit. Let's add some functionality to it. Suppose the user wants to see if a specific integer is in the list or not. Okay, so how do we do that? Well, there's a couple of things we need to do. Obviously, we need to do some function prototyping here. So let's do that. let's put it right under here, under handle largest. We'll say void. How about just handle find? We're going to find an integer in that vector, right? It's not going to change the vector, but I still need the vector. So I'm going to say const a vector of integers, and I want it by reference, and we'll use the v. Again, we don't have to use the parameter names in here, but I'm going to just use the v. So that's my handle find. Okay. Now, here we need to know, so here we need a function that's actually going to do the finding, right? And it's going to return a Boolean, true or false. I really don't want to know how many times it's there. You could certainly write a function like that, but let's just call it find. And what does it expect? Well, it expects that vector to look through. And again, it's a vector of integers, and it's by reference. And what else does it expect? Well, it expects the integer that you're looking for. So in this case, let's just call it target. That's the integer I'm looking for. So those are my prototypes. But before we even get to those prototypes, let's fix up the menu so that it displays that F, right? So I'm going to go down to display menu, and right after display largest, I'm just going to say cout, and we'll put an F in there, and we'll say find a number. All right, so that should display now. Now what do we do? Well, we need to handle that case in main, right? So we'll do it right after the largest, right here. So we'll say case F in this case, and we don't have to worry about the lowercase because it's going to be converted to an uppercase. And we'll say handle find, and we've got numbers. All right, perfect. So now what we need to do is we need to write these two functions that we prototyped. We need to write handle find, and we need to write the find function, these two. So let's do handle find first. Right? And we'll put it right at the bottom of the handle functions, right here, right after handle largest. And we could write a comment in here, but I'm not going to right now just to save time. So there's my handle find. Okay. Now what does the handle find function have to do? Well, it has to ask the user to enter the integer they want to find, right? So let's just call it target. And we'll initialize it to 0. And we'll just say something like cout, enter the number to find, or to search for, whatever you want to call it. And we'll read that into target. Okay. Now what do we do? Well, we've got that function we still need to write, the find function that returns a Boolean. So we're going to use that right now without even writing it because we know what it looks like. We wrote the prototype for it, right? So I'm going to say if find, and I'm going to pass into it the vector and the target. Let me get rid of some of those parens. That's it. So if find, that target and this vector returns true, then the integer's in there. So we could just write something like target was found. Else, target wasn't found. And I'll put some new lines at the end, some end lines. That pretty much handles that function. So what do we have left to implement? Well, we need to implement, let me scroll up a little bit here. We need to implement this function right here, the one that returns the true false value. And I'm going to put that all the way at the bottom with all my other good functions that are doing work. We'll do it right after get smallest right here. Let's write it right here. And there's the prototype, right? So what am I going to do here? Well, I'm going to loop through the vector and compare each element to the target. If it's there, I'm out. If it's not, I keep looping. And if I get to the end, I never found it, right? So we can do something like for, again, auto num, for each element through the loop will be called num. And there's my collection, the vector. And we'll just say if num is equal to my target, then I'm done. I found it. I'm going to return true. Now, if we get all the way to the end of the loop, we don't want to put this here. You want to put this here. We'll just simply say return false. Right? We never found it. So let's run this. Okay, we've got an error. It says number was not declared in this scope because it should be numbers. All right, hopefully you see that error right there. It was just a typo. And let's try it again. There's our run. Here you see the F in the menu now. So let's find a number. Let's find 100. Notice how it asks me for the number to find. Now the list is empty, right? So I should not find it. 100 was not found. Goodbye. What happened? That's an error, right? I should have never printed goodbye. Let's quit and see what's going on. Aha. Need a break statement. That's why we need to test our code. Forgot the break statement. Remember, with a switch, it goes to the next one. So handle quit fired. Let's try this one more time. Okay, so let's find 100. 100 was not found. We get the menu again. Let's add 100. And let's look for it again. So I'm pressing F for find. Let's find 100. Now it says 100 was found. And let's print the numbers. There you go, 100. So we've modularized our system into a series of functions. We easily added a new behavior to this, which is defined. And you can see now the code is longer for sure because you will also have a lot of comments in here. But you've got these really well-defined logical functions that are much easier to debug now. If there's something wrong, you can come in here and tweak it. You can also extend the behavior of the ad rather than having just one big main. And if you make any changes, you're going to put all your logic in there, and that main gets out of control very quickly. Okay, so hopefully your solution, it's probably going to be different from mine, and that's perfectly fine. Hopefully it worked out okay. And if you have any comments on it, please leave them in the course forum.